Good afternoon. My name is Sebastian. For those of you that do not know me, um, myself and Bern, who's sitting in the audience, we work at HITS. We think a lot about what to do with big simulations and big data sets. And now, first, I'm going to give you an introduction to our tools. And then after that, Bern is going to do a little tutorial to show you how to use them. Yes. By the way, this background here is back in the day when image generation on, I think it was ChatGPT. I asked it to do a million dimensional latent space. This is the interpretation from that. So I can give it to you. And you'll see I'll get to why this is related to the talk. So if you're an astrophysicist or a scientist more generally, this is how Wikipedia, this is the picture of Wikipedia for the scientific method. But apparently you should, if you're not an astronomer, you should be one. But we don't do science like this anymore, sort of. But so here you have somebody who is an observer. So in astronomy, these are the people that actually look at the real universe and take data. But something is missing, right? You don't do science just by taking data. This is an essential part, but it's not the whole story. So if you look at the typical diagram of the scientific method, you see here that the data is only one piece of the puzzle. And before the data, you have to form a hypothesis, right? So you have to build a model, and then you find data to confront with that model, and that's your discovery process there, where you falsify a hypothesis, right? And so in this bigger context, simulations are just very complex numerical that we need in many fields because the processes that we're looking at are very complex and nonlinear, and that happens very often in astrophysics and cosmology, right? So I think we're very used to working with simulation models. And so perhaps these people in the background here that don't seem to be doing anything, they're helping this guy with providing some simulations, right? And so I'll give you an example of a typical scientific question that we have from my own field, but you can think of it as related to anything in astronomy or in science in general. So the big question in cosmology is, does my physical model, my cosmological model, explain what we observe when we point the telescope at the sky? And it sounds like a very simple question, but it's in practice, it's very difficult to answer this. I hope you can see the pictures here clearly. Basically, this question comes down to comparing something like these two images, right? Here, one is a real galaxy, one is a simulated galaxy, and you see how complex simulations are getting there. Getting to the point where it's very difficult to tell these two apart. So sometimes in my talks, I ask people I play this game where I ask them which one is which, and most people can still tell that the simulation is the one on the right, right? So that tells you something about how good our visual systems are, because these two things are very similar, are quite similar. And so, but how do we actually do the comparison in practice? We cannot just do it by eye. And in reality, it's very difficult to do this. You cannot compare individual objects because galaxies are chaotic systems, right? So that means that by changing the initial conditions in the early universe, you can get two completely different objects, right? They diverge. So it's completely pointless to look at your favorite galaxy and then find another galaxy in your simulation and compare them, right? Because they might be drawn from the same distribution, from the same initial conditions, but they might look very different. So this makes this very complicated. And here you can see how this chaotic formation process, how we think it goes based on state-of-the-art cosmological simulations. This is the formation of a massive galaxy from shortly after the Big Bang until now. And you can see that there's a lot of things going on, and it's very difficult to describe it. But like I said, we need to compare instead the distributions of large statistical samples. And now we live in the big data era in astronomy, where we're going to get a lot of data. It's already coming in. This is from big surveys with LSST, Roman, Euclid, and the SKA, as we heard earlier today. So just to give you a taste of what kind of things are coming soon. This is Euclid. It's already taking data. This was one of the first early release fields. Just in this picture, you have 100,000 galaxies, right? This is one field. So in the end, it's going to have billions of galaxies, billions of pictures of galaxies with spectrum. And it's going to cover a third of the sky. And with the SKA, we're going to have most of the sky in radio. So looking at radio emission, including the cold gas in galaxies, so this gives us a completely different view of the same objects, right? So this is complementary multi-wavelength views, and the SKA is going to have also about 1 billion galaxies. So these data sets are going to be completely impossible to examine or explore manually or visually by hand. And therefore we need some more sophisticated tools for this job. On the other hand, simulations are quite different from observations. They're not only big as observations, as we call observations now. The biggest simulations now are petabytes in size, and that's expected to grow quite a lot. And in space, we're working a lot on growing these data sets and making them more detailed. But they're also very deep, and this is something that observations typically don't have. And by that I mean that you represent the same objects, or at least all elements, with many hundreds of different physical properties. So you can think of this as layers or channels or features if you think about it from the machine learning point of view. And you can have a lot of objects. So right now we're up to millions, but this is going to soon increase even more. This is sort of the state of the art in terms of large cosmological simulations, but this is already a few years old. This is the number of particles here, and you can see that we're getting close to the trillion resolution element boundary. And in the exascale era, this is going to be maybe 100 times larger simulations, 100 times larger data sets. It's going to be challenging just to move them. And then as these simulations are getting more and more complex, you start to suffer from this thing called Bonini's paradox, which says that as a model gets more and more complex, at some point it becomes so complex that it's useless, because it's as complex as the thing that you're trying to model. So you can think of like making a map so detailed that it's an exact reproduction of the city. And so therefore there's no compression of the information, and then it's impossible to use it. It's too big. This is sort of what data from a modern simulation looks like. You have all these snapshots in time of the evolution of a representative volume of the universe. This is an example with illustrious TND, about 10 billion resolution elements or even more. And then each of these is represented as a different feature. And then you can, for each of these features, you have millions of objects that you can examine in all of these sort of in all of these layers, you could say. And then you can zoom into each object and look at the structures within each object, right? So it's a hierarchical data set. So we've been thinking a lot about how to approach this problem of not only big but deep data in the simulations, and how to put it in the context of the scientific process, because what we want in the end is to do scientific discoveries. We don't just run simulations and take observations just for fun, although it's fun to do it, but eventually we want to understand the universe through this process. So in the future, we're going to have to move from this sort of standard model of your scientific sweatshop with your hardworking PhD students doing all the analysis, to actually using machine learning tools and using them on HPC systems because of the size and complexity of the data sets. And so you can actually also do in this way, you can also do model-driven discovery, which is a little bit different from your standard scientific method, in that here, instead of when you ask your question, you can run, let's say, a cosmological simulation. You can use that simulation to give you a hypothesis. And so your hypothesis could come from the simulation itself, the predictions of the simulation. And then based on this, you can collect data. And so you know very specifically what kind of data you need to confront that model with reality, right? So it's a much more sort of directed approach. And so the solution that we're developing in our group at HITS relies on this concept of representation learning, in which we're developing tools that can take both data from any cosmological simulation. They're meant to be universal and modular, so you can read the outputs of simulations and also large observational surveys. They're also multimodal, so you can use maps, images, point clouds from the simulations. You can use images, spectra, or data cubes from the surveys, put them together, feed it to sophisticated machine learning model that learns the underlying distribution of the data from examples. Machine learning is excellent at doing this through a generative deep learning model. So you can think of like autoencoders, for example, and then takes that data and projects it onto a compact, low-dimensional representation. In this case, it's the surface of a sphere. So you can see all the images from galaxies in the simulation, all projected onto the space in terms of similarity. So it gives you already like a organized latent space. And you also get catalogs, and you can select catalogs by similarity. And you can also interpret how the model learned to classify those objects or to place them on the sphere. So you get the latent space for free. This is sort of what this is a web demo that we prepared a while ago, but it illustrates how this visualization part, we're using Aladdin, which is an open source tool used by observers. The nice thing is it allows you to play with this hierarchical representation on a sphere, where the more you zoom in, the more tiles you see. So you can see arbitrarily large data sets. And when you zoom out, you just see examples of each category, sort of like an overall view. So here you can see all the images of each galaxy projected on the sphere. You can examine specific objects and get the metadata. You can also click on them and go directly to the data from the simulation for further analysis. And you can switch between the representation and the projected data set to interpret how the model learned this distribution. So this is quite powerful, right? Because this is a representation of the entire structure of galaxies, all the information contained in those images in 2 dimensions, right? So from an information perspective, these images are 100 by 100, so they're 10,000 dimensional objects, right? And you're compressing them to 2. And this is what machine learning allows us to do. And of course, our brains don't work in 10,000 dimensions, so it's much easier for us to do exploration and analysis here. So now I'm just briefly going to go through a couple of things that use cases or sub-use cases that we're thinking of for what we call our software, which is Project X for now, because we don't have a better name. How can you actually use this in scientific discovery, for scientific discovery? So if you're an astronomer, you know that this is a very common diagram. This is called the Hubble diagram, the Hubble sequence, the Hubble fork. It's basically how Hubble, almost exactly 100 years ago, thought that we could classify galaxies based on what they look like. Some kind of roundish, some more flattened, and then some have spiral arms. And depending on how wound up the spiral arms are, you put them in these two categories. Very simple model that he came up with, and it's quite powerful. And it's so powerful that we've been using it for the last 100 years, right? It hasn't changed. And it even percolated into how people in simulations think about galaxies. This is one of the earliest simulations. I think it was 1994, the first simulation to produce a galaxy. But you can see the galaxies here were so under-resolved that they were single represented by circles because they didn't have any internal structure. So we've gone quite a long way. The problem is that these representations have not evolved, and galaxies are definitely not points. As you can see in these images from some modern observatories, they're very, very complex objects. And so reducing them to single numbers is kind of a big waste of information, right? And this way of reducing them to single numbers depend basically on your preference. So instead, we can use these non-parametric unbiased descriptions that are learned automatically by the machine learning model, and that keep most of the information, right? Which might be very useful because we're investing a lot of resources into these calculations of the simulations, right? So you don't want to waste all that effort. And so, like I said before, because galaxies are chaotic, we cannot compare objects directly, so we need to compare the latent distributions. And so when we want to do inference, and this is something that's beginning to happen now, but it hasn't been possible yet, because it's very difficult to model the likelihood of a simulation. This is called simulation-based inference. It's sort of an emergent field, at least in galaxy formation and cosmology. And so this is the way that it was typically done. You would have your observation, you would have your data, and then you would reduce your data to one-dimensional summary statistic, like say the distribution of luminosity or mass or color of your galaxy. Then you plot it, and then you put that in your paper. You take your simulation, you do synthetic observation, so you turn it into something similar as what a telescope would see if it was a real object. Then you do the same reduction, and then you plot it, and then you compare 1D distributions, but you don't have any uncertainty because you don't have a likelihood. So it's very difficult to say statistically whether they're compatible or not. And this is what we've been doing for the last, I think, 30 years, most of the people that work in this field. So we aim to replace this with something much better that you can actually do proper Bayesian statistics with. And so instead, with the tools that we're presenting, you can automatically learn the joint low-dimensional representation of all of the data, the simulation and the observations. And then you can treat that as your approximate likelihood. So you can actually do Bayesian inference and model selection. And you can actually do this hypothesis testing that is sort of the main endpoint of the scientific method. And then you learn something about, in this case, galaxy formation and cosmology. Right? So this is the entire workflow that is contained there. But as I said before, you can go beyond that. What I call this model-driven discovery. So this is an example from my own field. So I'm very, very fond of this story. This is actually wrong. This was in 2015. So it was already 10 years ago that people developed this really cool sort of homemade telescope with a bunch of camera lenses. So it was very cheap. I think it only cost a few tens of thousands of dollars, but it was optimized to look at very faint objects very quickly, right? And none of the professional telescopes that existed back then could do this so efficiently. And as soon as they pointed it at some part of the sky, they weren't expecting this. They found this new class of galaxies. and this opened up an entire new field of research. Can you tell me where this object is that I'm talking about? So this is a normal galaxy. This is Andromeda. This is another normal galaxy, a smaller one. But the one that I'm talking about is here. I don't know if you can see it. It's almost not there. It's almost buried in the noise. And this is like an extremely faint and diffuse galaxy. It's very spread out. And none of the models that we had produced this or had an explanation for this. It had not, this has not been predicted. So people thought, when we saw this, people thought our models are all broken and we don't understand how the universe formed. This was one of the conclusions that people made. And then, of course, it sparked this. These are now called ultra diffuse galaxies, and people keep finding more and more because now we know how to find them. And this sparked this, as I said, it opened up a new field of research. Now there's more than 1,000 papers in the last 10 years, right? So this exploded. And of course, some of these papers were people that just went on to existing simulations and tried to look for these objects. And indeed, they actually found them. So it turns out that they were there all along, but nobody had bothered to check for these kind of rare objects in the simulations until somebody actually observed a real one and said, can you produce them in your model, right? And then the problem that we have now is that every simulation sort of produces a version of this object, but they're all different and inconsistent with each other, right? So, and it's not clear that if it's similar in one respect, it matches in all of the other respects. So it's still, the jury's still not out on whether the cosmological model is still able to explain these objects, right? And so, but you can think of this as a discovery workflow. First, somebody had to randomly find serendipitously an object that was weird in the sky, and you never know when that's going to happen, right? So this is not a very efficient workflow because you cannot target these objects. Instead, you could first look at your simulations, these large simulations, look for interesting objects there, outliers perhaps, because outliers allow you to test the distributions. And then you know how to find them because you have them in your simulations. You just go to a real telescope and target observations. So much easier, much more efficient workflow, right? So this is what I call model-driven discovery. And this is something that you can also do with our tools. You can sort of invert the scientific method. And the way you do it is because in representation learning, with many different models that we can use within our tools, like a variational autoencoder, you're trying to reconstruct your objects by first compressing them into a few numbers. And when you reconstruct them, you have this reconstruction loss. And what that tells you is how well the model learned to represent a certain object. So automatically, if you examine the catalog and you color them by the reconstruction loss, you can find the outliers. And so these are the strange things. So perhaps if somebody had done that with those simulations, they would have found these galaxies before people found them in observations. So it would have been more efficient. And so we think this has real potential to allow people to maximally use the information in the simulations. So just to summarize this part, we're entering the big data era in observations. We've heard people talk about already for many years. But we haven't heard so many people discuss the theoretical background that we need to understand those observations and to actually do discoveries, right? So this is where space comes in. This is why we're interested in running better simulations, but also in having tools to analyze and explore them. Cosmological simulations are particularly difficult to explore and interpret because they're both big and deep. But representation learning is an area of machine learning that offers an ideal solution because it creates this explorable, interpretable, compact representation, and it doesn't need labels. It learns only from examples of the data. And then it enables these two key things. You can do inference and model selection, and you can also do this model-driven discovery that I talked about. And if you're interested, we have developed a series of open source tools as part of this framework. They're all open source and publicly available here. And now I guess I'll first ask if anybody has questions before we move on to the second part. Yes.
Thank you for the amazing presentation. You see that when you're like working with the latent space, you can do interpretability analysis. How do you carry this?
So what I showed you,
And
here it is.
Define interpretability in this context. It's like local explanations of point data in the latent space, or like more the global behavior of the.
I think it's the first one, right? So because you have the latent space, you can do inference.
Yeah.
You can put any point you want on that latent space and create a reconstruction. And this is what I showed you. It's actually it's before the snapshot here. Yeah, here you can see it. This is the latent space. And here you can already see that the representation in this particular model does not capture a lot of the details of the guys. So you see they look like very fuzzy blobs, and they're all sort of the same color. And this was of course not meant to be perfect. This was a first prototype. So you can, from here, you can tell that the model did not learn the things that you're interested in, right? And if you flip back and forth, you can see, and here you can see how it arranged the data, right? How it learned to interpolate between the examples, for example.
Okay.
So you see there's like this yellowish stripe of galaxies here. These are sort of face-on spirals with a sort of bulge. I mean, there's already some morphological information that it learned here, but it's not perfect.
Yeah. So when you say interpretation, say like human interpretation, you can like sort of divide like explanations and interpretations in a machine learning context.
Yeah.
So this is like human interpretability in the latent space.
Yes, exactly. Yeah. I see what you mean. This term is.
You think okay.
Yeah.
Okay, no, that's good.
It's kind of an interpretation for us, but not precisely what it means in machine learning.
No, but that's amazing because it's interpretable in a machine learning context, but not interpretable for a scientist.
Exactly.
It's kind of useless. So that's even more amazing.
Yeah, I think this is why I like this type of models, because you see how they're learning. It doesn't mean it's easy to have it learn.
Yeah, but it's useful.
Yeah. So, so we're trying to make this modular, so you can like plug in whatever model, because things change so quickly in machine learning. Newer models are showing up all the time, so you can just plug it in whenever you need something new.
Well, these are another pre-question. You try also other like a diffusion flow, other kind of.
Not yet.
Okay.
But this is on the list.
Okay.
So Bern here has been very busy working mostly on the architecture, the sort of the overall architecture. But once we're done with that, we're going to experiment with different ways of learning, like transformers, diffusion. The latest thing. This is what I'm showing you here is just a variation of autoencoding. So it's relatively old in machine learning terms. Yeah. It's old, but it's very simple.
Yeah. Okay. Thanks so much.
Okay. Hi, everyone. Well, my name is Bernd Rode. I'm a software engineer working together with Sebastian in Heidelberg at HIPS. The others in the group, Kai is the group leader, and Andreas Fender-Bromont, also working in our group. Sebastian has introduced the topic more from the scientific perspective. I will show you now the software works and how you can use it. So I will start with a brief overview over the Project X workflow. And then I follow with 3 modules we use in this little demo. The first one is for the data preprocessing called PEST, then the training engine called Spherinator, and the inference producing all these reconstructed images called Hipster. Let me try to make this live demo with the Jupyter Notebook. And after then I will show an example for multimodality using, instead of images, 1D spectral data. And in the end, I will outlook how we can orchestrate our workflow on a cluster. So all these materials, so the presentation slides and the demo notebooks are publicly available at GitHub. Find it at this link. And also here are links to these 3 modules we are using it with. And there's also a user documentation available. You read the books. So the documentation is part of the repository of the specific module. Okay. Our workflow is divided in 3 tiers. So the first tier is producing the input data for the training. It's preprocessing or test. And we extract the data from the cosmological simulations or from the observations and produce input data for the training, but in different formats. So we can produce images, point clouds, data cubes, time series, or spectra. And all these are stored in a unique data format in Apache Parquet. This is, I will show it. The second tier is then the training itself. Here different techniques. I will show here in the demo the Spherinator, which is a deep learning technique. We also have a Cohunen map, it's a very old one, thing we can integrate. And not published yet is the Spherinator or Actograph map, which is using a graph for geometrical deep learning, especially for point clouds. The data is exported also in an open standard called ONNX. And this model is then used in the inference part. It is our hipster. This hipster is then producing all these images, which we can visualize in the third tier, which is responsible for the visualization. Here we can, in the demo, I use Aladdin or Aladdin Light to visualize the latent space. This is optimal because we have a sphere and LED light is perfect for this zooming in and out in this sphere to visualize all these pictures. So as I said, the preprocessing is using the snapshots of the simulations and extract and select the data and produce different outputs. And this is stored in an Apache Parquet. So this is a tabular storage, very efficient, especially when you use Apache Arrow, and it is very fast. And Apache Arrow is a memory, keeps all the data in memory, and it is available and it works together with PyTorch or TensorFlow, and also with other languages. Python, C++, Rust, all these important languages. You can easily create a model in PyTorch and then use it in C++ or in Rust without the training framework. You only need this ONNX model. Okay. Then Spherinator is our training engine. Here we use this relational autoencoder. We have the input data, and this is the dimension of this input data is reduced into this Latin space. And from this Latin space, we sample a point, and the point is then reconstructed with the image again. And the model is trained so that the input and the reconstruction image is very similar. In the background, we are using PyTorch lighting. So Spherinator is providing all these architectures, the data loaders, the distributions, but in the background then is PyTorch lighting called. Instead of plane in the lattice space, we are using a sphere. Therefore, we need a different distribution function. And this is the formula for this. We use the power spherical distribution. The very important part is we have a direction, which is the location on this sphere, and this concentration, which define the width of the distribution, like a Gauss function in a plane space. This is the same for a sphere or a hypersphere. So it is also possible, if you need more dimensions, you can go up and use a hypersphere. Okay, when we have our trained model, we produce then all these reconstructed images. And therefore, we use this QPix framework. And we have here the coordinates in the sphere, and use these coordinates to reconstruct the image, which then is visualized on this tile of the sphere. And this is exactly what is used in Alabin Light. Okay. Then we start the demo. You can also do it when you go to this repository. There's also a link to Colab. If you have a Google account, you can do it in Colab, or you clone it and run it in VS Code or in Jupyter Hub. All this is possible. There are also more demos available. For example, for the Gaia project, they are doing more things. But I will show you this one. So we make the training. First, we have to install the Spherinator package, if it is not already installed. So the current version is 0.4. And as input, I have a very small data set for this demo, only consisting of 200 synthetically images from the illustrious TNG simulation. So we download directly here the Parquet file, illustrious Parquet from Google Drive. Okay, and then we can use PyArrow, this one Apache, read this file we have just downloaded, and take a look on the scheme. And then we see we have one data column, which is a list of list of doubles. And we have some metadata, the simulation string, the snapshot string, and also the sub-halo ID. And also there's in the metadata section stored how the real shape of the data looks. So we have 3 channels, and the images have the dimension 128 times 128. We can also migrate now this pi arrow database to pandas, only to visualize first the table. See here the first 10 galaxies with the data array and the metadata. And then we can also visualize how they look. I'm just printing it here. So these are the first 25 images for our training. Yeah.
Sorry, can you show again what the link to the collab is? Because Nathan was asking me.
Ah, sure.
Sorry, I can't find it anymore.
You can use here this link when I click here in the README.
It's
Here you can run the demo.
This is from the public data set.
Can you show me the link again?
The link, yes.
But you should
Sorry.
be able, soon you should be able to generate.
I
data.
can remove
So we're
this.
still-
You can also use the QR code. You have it?
Yeah.
So nice pictures of galaxies. But now we have to define our model. Here we is the first time we need a Spherinator. We import the models of Spherinator, and we define a variational autoencoder model. And here I can choose a convolutional network, for example, as encoder. But here everything is possible. You can also use ResNet or transformers or everything you like. We have some layers defined here for the encoder. The same is needed for the decoder part here. And here we see the dimension of the latent space. I have 3 dimensions, but only 2 are independent because I have this formula for a sphere. So I have these 3 coordinates, but 2 of them are independent and 1 is dependent. But I have to define here 3 as dependents, as number of dimensions. And also important is this beta factor. This is used for the variational part, which is a balance between the reconstruction loss and the Kullback-Leitner divergence, which is responsible for the distribution. Okay. I have to execute it, as it is defined. As next, I need a data loader for PyTorch. Here I import data section of Spherinator. We have written our own Paquet data module. You can do some other pre-preparation like a normalization or something. You can also define which column of the Paquet file is used for the training. So we have also stored some metadata, but I only want to use the data column for the training. And then I define the trainer itself. This is now coming from PyTorch Lightning. We run only 10 epochs on this little GPU card on my laptop. And when I start this, you see a short summary. and the training begin. We are now in the epoch 4. Very small data set, only 200 images. So this is now stopped. And I have now a model in the PyTorch checkpoint file. And I want now to export this in our general ONNX format. Here I use also the torch export function. But I only export, no, I don't export the whole model. I export it, split it only for the encoder part and for the decoder part. So I have now two files, two ONNX files without this variational section. This is not needed for the inference. Okay. Everything was successful. And I have now my first model as stored as ONNX. And we can go on with the inference part. Now this Spherinator package is finished. We don't need PyTorch anymore. We can everything do, for example, in Python with Python NumPy. Okay. We start again importing the hipster module. And then the first task is to produce the reconstructed images for our sphere, for the sphere in the latent space. This makes the HIPS generator. I need a decoder because this is responsible for the reconstruction. So I need the coordinate in the latent space. And from this coordinate, I produce my image. And here I simply forward it to an image plotter. If I have a different format, for example, for this spectra data, I need here a function which produce an image out of my data format. For example, a graph image. Okay. We can also let this run. And as a second task, I want to produce a catalog. This means this is the encoder part. I want to know where is, on which location is the input data on my sphere. And here I want to see a little point in my latent space. This I call a catalog. And you see here, you need the encoder part and also the input data again. For the HIPS generator, I don't need the input data, but for the catalog. Okay. And when this is done, all the files are generated and can visualized with Aladdin Light. And Aladdin Light has now also a plugin for Jupyter notebooks. I will use it here. Can install Aladdin and define the output section of the HIPS file and the catalog. And you see here the first sphere. This looks not very nice, but this is not surprising because we have only trained it for 10 epochs. To show you a fully trained set, you can, in the next part, you can simply download the models of a full trained model, execute the HIPS generator and the catalog generator again, and visualize it. And then it should look very nice. So you see the Latin space, and you see also that similar galaxies are located nearby. I don't know. I think the catalog is missing. Maybe there is a bug of other light, or I do something wrong. But you can also load it here manually over overlays, catalog, VO table. And where is it? No. Full trained. Here, this VO table. And you see where the input data is located. Latin space. But Sebastian has showed this already. Okay. This was it for the Jupyter demo. But as I said, there are more available in the repo, also using the pre-processing module. You can also visualize the UNNX model. And this command line interface is also used in the other parts. So just try it out. Okay. Here I want to show a second example where I not using images, but 1D spectra from Gaia. This dataset contains over 200 million spectra in a continuous storage using 55 parameters per spectrum. And when I train this, you see it here with a very large catalog. I will hide this, and you see now on the sphere different spectra in the same way like the galaxies. So displayed similar spectra are displayed each together. Okay, and this is here for different data format. You only have to change the encoder and the decoder. You use 1D convolutional network, and for the hipster, you need this function which creates your image for your data format, so from a normal spectra to an image. Okay. Then very brief, we can first, this Jupyter notebook is only to show you the features, how this is working together. In production, you would write one single YAML file with all this configuration. You define your model, you define your data loader, trainer, and all steps, and call it with one command. The same for the hipster. And when we have a larger workflow, we can also orchestrate this using Flight. So Flight is a cloud-native framework. And the advantage is that every task is executed in a Kubernetes cluster in a defined environment using a pod. And I can also define the resource where the task is executed. For example, I can execute the training on a big GPU card and all this inference things or exporting things on a CPU node. So it's very easy. You only have to write a Python script, and each function of the script defines a task. You can then write in front of this function where this task should be executed and in which environment. The best way is using a Docker container. And the data is transferred over an object storage. So it's like a Python. So when you have a Python output and bring it as input to the next function, then the output is simply stored in an object storage and read again for the next task. But you need a Kubernetes cluster. If this is not available, we can also use Streamflow. Here you have no dependencies. You simply write your workflow and can also execute this on different clusters. But we have heard this in a previous section. Okay, so I will summarize. I've shown you this Project X workflow, which is very modular. So each module has its own repository. All are available at GitHub with all the dependencies. The important thing is the interconnectivity, that every module can read the data, and this the unique format is this Apache Parquet. And also for the model, yes, this ONNX format as unique storage. I briefly showed you this workflow orchestration. Here you find a link for another seminar I had discussed this more in detail. And you find the full prototypes for the illustrious TNG and Gaia dataset at this address. This was all. Have you questions? Nothing. Okay.
I think Marisa had a comment about one of the.
Yeah, if you can just go a slide back, slide on it. Concerning
Yes.
now the model exchange, just for those that might be interested, we have training on that. So on Space YouTube channel, you can have an insight on what the open neural network exchange model is about. So just to add one extra element to what Sebastian Werner already presented.
Yeah.
Was that?
And it's also very general.
By Andreas Fellner, by It's again. So if you're interested to know also something about this, you can find it on the YouTube channel of Space. It's more or less 40 minutes of presentation, so you can just add an extra element.
Maybe we can link it on the slides as well.
Yeah, I can do it. Sure. Okay, and thank you.
Thanks very much.
Okay, hi everyone. For those of you who don't know me, I'm Marta, working here in BSc in the HPI group, along with Pablo, who will present later on. So, sorry for the interruption. As I was saying, Pablo and I, we work together here at BSc in High Performance and Artificial Intelligence department, and we are also involved in the space project. So today we are going to give you an overview of our work in this task of machine learning. So first, we will see some theoretical concepts that I'm sure that you already know, but I think that it's interesting to show. We have a second part in which we will present the pipeline that we have built. We will show you as well some results and a small demo. So the main task that we are covering within the space project is to infer key physical properties of galaxy clusters directly from observations. So to do so, we use cosmological simulations. I'm sure that you have worked with some of them, and we generate 2D maps of features. Here we have the velocity dispersion and the intercluster light, but our pipeline also support other kind of features. Once we have generated the two-dimensional data set of maps, we train deep learning models in order to predict from one feature, go to the other. So we are giving as an input velocity dispersion maps, and we are predicting the intercluster light. All of these, although, fulfill a more general purpose, which is to understand the origin and evolution fate of the universe. So we could say that this is really an important task to work in. I didn't say, but this is already a work in progress based on previously work by Ilaria Marini. So we are working together with her as well. So in order to do so, we are working with hydrodynamical simulations. Those are computational simulations that model the behavior of the matter, mainly fluids and gases, under forces like gravity, temperature, and pressure. So here on the right, we have a list of 6 cosmological simulations we are working with. So right now we have data of these 6 simulations. You may be wondering why we are not using real data. Of course, real data is incomplete, noisy, and very limited, and doesn't allow us to experiment with it. So we decide to use these simulations. In particular, within these simulations, we find the galaxy clusters. Those are just a collection of galaxies. Here we have an example just of a bunch of galaxies from Magneticum. The fact that I can do this zoom in, because this galaxy is this one. The fact that I can do this zoom in is because these simulations have parameters such as the box size, which is the size of the universe we are simulating. And also we have the spatial resolution, which is the level of detail we have. Several different simulations, they have different boxes size and different level of detail. Within these simulations, we are working with halos, subhalos, and particles. Of course, you have already heard about them. Just as an example, here we have got one halo from Milky Way. So this big circle represents the boundary of the halo. And within this halo, also called FOF, friends of friend, because of the algorithm, we find smaller structures or satellites, which are the subhalos. And within the subhalos, we have the particles. Since the particles and the subhalos are bonded together by gravity, these particles stick within that region. As input features to build the maps, we are using the information, or as I mentioned before, halo, subhalo, and stellar particles. So in general, we pick up the coordinates of the 3. And for the halo, we use R200. For those who are not familiar with R200, here on the right, here, well, this halo and the primary subhalo, which is the most massive one, this is marking the boundary of where the gravitational is bigger. And when you go outside, the particles start to spread out. The gravitational is not that strong. Then we have the mass 200, which is a mass contained within that radius. And in the other side, in the subhalos, we work with the stellar mass, the mass of the stars. The stellar half mass radius, which is another radius again, where we can find the half of the mass contained. So this is the distance where you can find the half. And for the stellar particles, we use the mass, the velocity in 3D, and the coordinates. All right, so as for the features, as I mentioned before, we work with velocity dispersion and ECL, intercluster light. Those are examples of maps that we have generated. I will begin first with a very intuitive definition, and then we will move to more details about the ECL. So the velocity dispersion can be understood as how spread out are the velocities within a star, within a cluster, very easy. Also can serve to answer this kind of question, to see if the cluster is more relaxed, is more stable or not, how is evolving and how is moving. In the other side, as output, what we want to predict is intercluster light, is the focus of our work. There are several types of definitions depending on the detection mechanism that you're using. We will see why. But on our side, we have defined it as a diffuse faint light coming from a stars that they don't belong to any cluster. There are several studies in this matter because this is a huge file of research, but astronomers have seen that when the velocity dispersion goes up or it's higher, this leads to more stripping of the stars, more interactions, more mergers, and leading to a more higher intracluster light. So why this is happening and why this is important? As I mentioned before, the ECL is primarily built by tidal stripping, mergers, and interactions. Here we have a visual example. This is a tidal stripping. In general, when you have a tidal stripping, this like you have two objects and one is absorbing the other, but this is happening super slowly and in a gradual process, I would say. But in the other side, when you have mergers, this is a real picture from Hubble telescope and the generated artificial real image, I would say. When this happens, since this is a more violent process, the process is very destructive and it happens faster. So coming back to our question, why ECL matters? ECL is important because it's a way to track the history of our universe, to see how galaxies and subhalos have merged. And then this makes us think that ECL is some sort of fossil record of this past history. Another important thing to consider is that ECL is hard to detect. This is first mainly because of the nature. As I said, it's faint, diffuse light, and also it's easily masked by other brighter structures. So in order to show this, I wanted to include that image. This is a galaxy, and in these two images, we have the BCD and the ECL. This is a difficult process because the BCD, which is the brightest cluster galaxy, if you see, this is the center of the galaxy, and in the surrounding we have the ECL, and this process is really difficult to separate because the BCD is really strong. On the other side, apart from this nature, we have seen that there are discrepancies regarding the definition. As I said before, depending on the method that you use to detect the ECL, the structure of the ECL change. And also the dynamical state of the halo may have some impact in the ECL form. There are several detection mechanisms to detect the ECL. Here is just a list of the most popular ones. I will just give a clue about each of them. Maybe you know some of them. So the first one, the surface brightness thresholding. The scientists they define like a brightness cutoff, and everything that is fainter than the threshold is considered ECL. In the second one, the planetary nebulae, they analyze through a spectroscopy. They analyze different star populations, and they see the coordinates and the velocity. Depending on how far and how fast these objects are moving, they consider the planetary nebulae to belong to ECL. I'm oversimplifying, okay? What else? The image decomposition, as the name says, is a numerical method. So they pick up the images and, the stars, and they try to do some sort of subtraction. Whatever is left, again, is considered to be ECL. The stellar population analysis through spectroscopy, very similar to that one. In that case, they analyze the spectrum, well, the spectra. They analyze, for example, the age, the metallicity, the velocity, and they try with this information to try to classify into BCG and ECL again. The last one, which is the one that we are using, the kinematic separation. This is a dynamical method. In our case, we are using a random forest trained on a kinetic separation. The algorithm is known as ECL subfind. Maybe you have heard about. With this method, what we do, after Pablo is going to give you more details, but what we do with this ECL subfind, we take the stellar particles, we compute the velocity, we normalize we take out the velocity of the cluster. So we have the velocity respect the origin of the halo. And then we try to separate the velocity of the ECL particles and the velocity of the BCG. We use a double Maxwellian distribution. So it's a method that relies on the assumption that particles belonging to ECL and particles belonging to BCG, they have different velocity distributions. We have decided on the top of that, build a pipeline with deep learning models, well, machine learning and deep learning models that I will show you in a few minutes. So why we decided to use machine learning models? Of course, we are working with them, so we know how to use them, but there are several advantages in favor of adopting this approach. So first of all, in the first case, we want our results to be scalable, consistent, and reproducible. So no matter the data that we are using, we want the models to be reproducible if you want to execute them again. The machine learning models are pretty good working with huge data, which is the case, and they are scalable. So it's not a problem when you want to deal with a big data. We want also to be able to run our pipeline with different simulations, more features, and different combinations of input and output. Also, they do a great job trying to discover or to deal with nonlinear relationships. And lately, we can transfer, having these sort of models, we can transfer the knowledge from simulations to real observations. All right, so here we have a diagram about the pipeline. I'm going to explain briefly what we are doing. So as you can see, we have two parts, the data generation part and the model training evaluation. So the idea is to, in the data generation, what we do is through several configurations, we choose the hydrodynamical simulation, we choose the features of the halo, subhalos, and particles that I have shown before. And we define other cosmological parameters, Hubble, spatial resolutions, and so on. So as output of this process, we have 2D maps, one for the input and one for the output. These two maps then are used to train deep learning models. So the problem that we are tackling in the second part is different. In the model training evaluation, again, we have a different configuration. We choose a model, we choose the data sets, and what we are trying to do is to generate the same maps of the output, and we compare them to perform the evaluation. All right, so in the second part of the model training, our I would say general goal is not to have small models trained on different simulations. So what we are doing is to generate the data sets, choosing each simulation, and try to train a foundational model. So right now, as I mentioned, we are using the velocity dispersion, and we are focusing on predicting intercluster light, but there is no problem in adding more simulations or even more features on the problem. So we are wondering, we are considering to add in a near future the metallicity and dark matter mass. This is information that we have in all the simulations, so it's something that we can do. All right, why we want to do or why we want to perform in that way? Of course, this is more this is faster and more flexible than using numerical methods, as easy also find, for example. Again, since we are using machine learning, deep learning, we have the pipelines. This is reproducible and scalable. This simulation agnostic because the pipeline is built in a way that you define a halo, you define a subhalo, and what is a particle and how the data collection is done. So you can add more simulations. This is not an issue. And then, of course, using deep learning models, we are able to tackle and work with a more richer feature space than just working with, for example, velocities. Let's move. All right. Something also that we are considering to do, apart from inputting the maps, we want also to try to include as input as for the models, the interlopers mask. We are saving them, but right now the results we are not using them. And also we consider to use the random forest uncertainty. This is an error of the model because maybe we have the ECL mask, we have the velocity dispersion, and this the level of confidence of that map is low, and this information is not being considered by the model. So this is something that we are going to do. Of course, we don't have to focus in this combination of features. Since we have the pipeline, we have the models, it's just a matter of coding and implementing each input feature and output feature. So something that we have been talking with Sebastian is to try to inspect the relationship between the stellar mass density and the dark matter density. So there is a very big room to work. All right, let's dive into the first part, data generation. So as I mentioned before, the goal is to generate the 2D maps. We have the configuration and we have defined 3 steps: the data loader, rotation, and map step. They are very intuitive, as you can see by the names. Let's dive into more details. So this is the data loader part. What we do is to, of course, load the simulation data, illustries, magneticon, whatever. For that, we move all the data into our cluster. We filter the halos and subhalos by mass because we want to work with just massive halos and subhalos. This is because if we work with massive halos, the concentration of the intercluster light is bigger, and we have more particles, and the feature space is richer. But this is something that maybe we will take out if we work in the Sebastian case. Also, we want to include in the maps the overlapping subhalos because we want the maps to be realistic. So we need to detect them. In order to detect them, we need to be smart because this is an expensive computational task. So for that, we use a KD tree. Not sure if you know what it is. KD tree is just a binary tree where you split the space and you take first the x coordinates, you split in the tree, and then you consider the rest of the coordinates, the y and the x. So you can perform queries in a logarithmic computational course. So it's very fast. In a visual way, what we do is, if you can imagine that this is just the halo center. So we draw a sphere with a radius of the double of the 200 R200, and we add all the subhalos in this sphere. Well, we will add them when we compute the maps. All right, so what else? We take for each halo, we do some sort of loop. Of course, we take the particle data, the stars. This is important. Apply periodic boundary conditions. We observe that when we use raw data, sometimes when you normalize the position of the particles, so you have the center, you have the particles, and you center them, sometimes there is a risk that you go out of the box. And when this happens, the coordinates, they're going to be wrong. So you need to correct them. We compute the velocity dispersion and we run the classification. This is the random forest I mentioned before. We will see them, we will see some results. We estimate the transition radius. This is also carried out through experimentation, because at the beginning, when we use, for example, Illustris or Magneticum, whatever, we don't know the transition radius of that simulation, so we have to approximate it. On the right, just for you to have a visual idea, this is a plot of the cumulative mass of ECL. This is ECL, this is BCE. So we want to know at which moment, at which distance, the ECL starts to be prominent. So at which moment we have more stars on the ECL than on the BCG. Okay. And finally, we merge the particle data. We pick up the particle of the overlappings and the ones that we have for that happen. Okay, we move to the rotation step. This is very like intuitive, so I'm not gonna show any slides. Just pick up the particles, you choose like a vector for the direction, and you rotate the particles with respect to an axis. So it's not a big deal. In the final step, the map step, this is the moment in which we start to generate the 2D maps. So first of all, we need to compute the beams. So depending on the number of beams, the images will be higher or smaller. So how we get the beams? This depends on the cosmological, the cohomology resolution. This depends on the simulation that you have chosen. The scale factor, you can choose that. The transition radius that you have found. And would say that that's it. Yeah. So the resolution is the most important thing. Then the model needs to take into account different image sizes coming from different simulations, but this is not an issue. So once we have the maps, we compute the statistic depending on the velocity expression on the ECL. We pick up the particles, the value, and we compute the mean. Also, I didn't mention, but we have to identify the interlopers. The interlopers, you're not going to see them here because we save them in a separate channel. But those are all images coming from, I think, the Yanoka or the Yanoka. So the interlopers are these black dots. The interlopers are just considered like foreground, background objects. When you pick up the line side, they are objects that are in that line, but they are not bound to the halo, so they are excluded. But we are saving it in a separate channel, and we aim to introduce them to the model prior training. And finally, once you have build maps, we crop them, we pick up the center of the image, and we run three like shifts. This is just for data augmentation purposes. And then finally, we have our beautiful maps. Before we move on to the models training, I just want to give you a brief, I think I didn't mention, yeah, here maybe, how to interpret the images. I think I didn't explain. So velocity expression is very easy to understand. It's just the velocity expression of the particles in each pixel. But in this part, in the ECL, the way to interpret this is if you pick up some region, this is like a percentage, like a fraction. It's the amount of particles which belong to the ECL. So if I pick up, I don't know, the part that is more in purple here, 40% of the particles there fall in that region belongs to ECL and 60% to the BC. All right, so now we can move to the models training evaluation. Pablo will introduce them, and finally, we will have the demo.
Yeah.
All yours.
Thank you, Marta. Okay, so I will cover the second part, which is once we have gathered this data using the pipeline that Marta just explained, how do we train models on it to extract meaningful results? Okay. Before we do that, let me explain the base algorithm that we are trying to replicate, which is this famous ECL subfind. Essentially, as Marta mentioned, ECL is very difficult to find or detect. Luckily, in the literature, there's already people who has carried out the effort of mapping particles to either BCG or to ICL. This is the ICL subfind algorithm. Essentially, how it works is you center a sphere around the center of the halo, you compute the gravitational potential field inside this sphere, and then you go through every star particle, and then you compare the kinetic energy to the potential energy. And then you will temporarily label that particle as belonging to ICL instead of BCG if the kinetic energy is bigger than the potential energy. Now, what's the catch? The underlying assumption is that the velocity distributions of the ICL particles, they have a greater variance than those of the BCG, which have colder dynamics. So essentially, we will be fitting the BCG particles and the ECL particles into a double Maxwellian, okay, which is essentially this distribution. So as I was saying, we have centered a sphere around the center of the halo. We have computed the gravitational potential field, and we have compared the kinetic energy with the potential energy at that point, and we have labeled particles as belonging to BCG or ICL with respect to that. What does this give us? This gives us two groups of particles, and we can fit a single Maxwellian to each one of these groups of particles. And this is the two lines that you see here. Now you take the whole velocity distribution of all particles in the halo, which contains both the BCG and the ACL, and you fit a double Maxwellian, and then you compare both distributions. If they agree within a threshold, then you finish the algorithm. If they don't agree within a threshold, then you are forced to choose another radius, fit another sphere on the center of the halo, and then compute everything again. So this numerical algorithm is essentially very, very costly to compute. It gives us a ground truth to work with, but it's not practical. So as Marta mentioned, there's the possibility of training machine learning models on the outputs of this algorithm, such as the random forest, which we have used to generate the ACL maps. Now the question is, can we do the task starting from simpler information, which is just going to be the 2D maps of the velocity dispersion? So can we replicate the results of ICL subfind as an image-to-image translation task, where with a simple 2D velocity dispersion map, we're going to be predicting the ICL fraction? Okay, this is what we want to solve. So essentially, we have gathered the data, we have the maps of velocity dispersion, and we have the map of ICL. Now we're going to be training models on this image-to-image translation task. Essentially, just to give a brief overview of how this type of tasks are dealt with in the field of AI. Essentially, we use kind of encoder-decoder architectures, such as the one that Sebastian mentioned in his work. Essentially, we're going to have two neural networks. One is going to be trying to encode the information of the input into a lower dimensional space, and then we have a second network, which is going to be the decoder, which is trying to convert this information from the lower dimensional space to reconstruct the original input. This is an encoder-decoder architecture. Okay, but we can do something else. Instead of trying to reconstruct the original information with the decoder, we can try to reconstruct related information, such as, why not, the ICL. Okay. So this brings us to the first type of models that are usually used for this task. This is the UNet. Essentially, this is how they look. This is going to be the encoder. Essentially, it just has convolutional layers, which just apply filters to each part of the image. You just have to think that a convolutional layer is looking at local patterns inside the image and filtering them. And then we get to the latent space, where technically we have gathered all the necessary information to reconstruct that image, or to construct the ICL map. Okay, so this is the most basic architecture that people usually use for image to image translation tasks. This is gonna be also our baseline. Okay, there's some other elements such as residual connections, which just jump over the construction of the lattice so that the information in the input is also present for the decoding. This is in order to make the training more efficient. There is improvements of over the unit, such as the attention unit, which just adds attention maps, okay, which simply allow to pass the information from the input and compare it to what we are generating here. So essentially, what would be happening here in this attention gate would be, okay, I have a proposal of an ICL map, then I'm going to compare this with the original velocity dispersion map, and I'm going to be looking into which parts of the velocity dispersion map tell me that there should be a certain ECL fraction in that particular point. But there is more complex architectures that we're going to be trying to compare against. There's the trans unit, which essentially you substitute the encoder by a transformer. This is because it allows us more flexibility with respect to scaling. So if we have more data, we are entering exascale era, and probably like the amount of simulation data that we will be able to get our hands on is going to grow and grow and grow. So maybe at some point we will want to grow our models. Units type of architectures, they don't scale so well, but transformer-based architectures scale better. So why not try a transunit to see what's their performance compared to units? And then we have a final architecture that we're going to be working with. This is the Mamba. They are data state space models, which come from control theory, where they are used to model dynamic systems. Okay, essentially, how it works, it's a sequence-to-sequence model. They are not originally created to work with images. And essentially, in every step, in every iteration of the model, you are computing a hidden state which represents the change on the system. Okay, and then like you do recursively this, the amount of times, an amount of times equal to the number of steps that you have to take to process your sequence. And then you consider the images as sequences, and you go over them like in a forward and a backward direction. Essentially, how they work is like they look into local patterns, but they also keep a memory of the global pattern, which is the hidden state. Okay, so where the unit looks mostly at local information, and then like as you make the model more like deeper, you allow the model to have like increasingly grow to understand increasingly abstract concepts on the input. With the Mamba, you're gonna be keeping a sort of like a long-term memory, which codifies the global information of the picture, while at the same time you are paying attention into local patterns. So we think that Mamba could be like a very good a model for this velocity dispersion to ICL task that we want to face. So those are the models that we are working with minor modifications to like all the research lines that we are, all the research ideas that we are thinking about, such as increasing the number of channels, adding uncertainties, predicting dark matter distribution, and so on and so forth. Okay, with minor changes to the architectures, we can do all of these things in a single go. So let's go to the experiments. Essentially, the questions that we want to answer are the following. First is, can deep learning models effectively learn to reconstruct ICL maps from VD? Otherwise, from velocity dispersion. Otherwise, there's nothing to do. The second question is, how much can we scale training data to scale results? That is, if we can gather more simulations, will our results get better, or is there a limit? Third question is, are deep learning models an efficient algorithm for ICL prediction? Essentially, we want to know if computationally they make sense, right? Because otherwise we could just use ICL subfind, which is a deterministic algorithm, which is also very robust, right? Finally, the last question that we want to answer is, do these results generalize across simulations? So if I have trained my model on like, let's say, Illustris, can I use my model to predict the velocity intracluster light in some other simulation that I'm working? Okay, So let's try to answer these questions. As Marta said, like this is still work in progress, so we don't have like all details, but I will try to answer them as much as possible. So first, how are we going to evaluate the results of the experiments? Where we're using several metrics for image reconstruction, right? So we are converting the task of predicting ICL fraction into, creating these maps where in every pixel we have the ICL fraction. So we can use metrics for image reconstruction. There's the famous binary cross entropy, which we're going to be using as our training objective. There's the robust mean square error. Essentially, the mean square error tells us the difference between the target image and the prediction. The problem is that the mean square error is not very stable. If there is some areas where there is a high divergence, this impacts the metric. So the robust mean square error uses a sliding window approach where we are moving a window. We use, I think, 4x4, and then we are looking at the mean square error in the local regions, and then we compute the error. The relative average spectral error is going to be our reference metric. Essentially, it does something similar to the robust mean square error, but considering several channels. As we're going to be computing information that is different for different channels, such as the interlopers present, such as the uncertainty maps, such as potentially in a future the dark matter distributions, we want to have a metric that is also like robust across channels. Okay, so essentially the relative average spectral error computes the robust mean square error over channels, and then computes the mean, balancing it by the average pixel activation. Okay. Yeah. So let's go to the results. Well, this is the first result on the Dianoga. So we are evaluating on halos from the Dianoga dataset. Essentially, the baseline is state-of-the-art algorithm, which is UNet in the background that was trained also on Dianoga data. Okay, and that we are using as reference. The flows are computed per single forward path. Okay. So essentially, we have here several models. Just something to mention here with Russell, like lower is better. So we see that the UNet is the most efficient model. Okay, but we also want to have a look into the flows. We want a model that is also as efficient as possible. More results. What happens when I increase the training data? So here, what we have done is we have grown our training data set, and we have included data from Eagle, from the Eagle data set, and also from Illustris. We see that when we grow the num, so in the previous slide, we're using around 80 halos. Okay. Here we're using several thousand halos. We see that when we increase the amount of training data, several orders of magnitude, all models kind of converge to like similar results. Okay, we see that the objective loss that we are using for training, which is the binary cross entropy, actually doesn't have like it's not fine-grained enough to allow us to discriminate between models. Okay, and yeah.
So because your maps are normalized 0 to 1, your RMSE is basically a percentage units, right? So this is like 2%. Yeah.
You mean here?
Yeah.
Not exactly. This is well, yeah, you could understand it as the average agreement among patches of the predicted image and the target image. Right.
But yeah, but this is I'm trying to figure out how big this number is if you look at the images.
So this number is average, right? So it gives you, so if you fix a 4x4 patch of the image of the predict, so you are reducing your image to just being by 4x4. This is essentially the divergence between those pixels in the predicted and the target, and you are taking the root square as well.
But the pixel values are 0 to 1, right?
Yeah. They are ICL fractions.
So that means that this is percent, like 1.8%.
Mm. Yeah. Okay, next plot, I think this answers the question of what happens when we scale data, like do our results improve? Just look at this. I want you to look at these two curves here. Okay, here we are comparing the UNet and the Mamba, as I introduced it before, and we see how the UNet is essentially better. We got lower losses for lower. Okay. Something else to mention here, these results are evaluating on a different simulation than the one that we trained on. So essentially, we are also answering the question of, do these results translate along simulation? So what about this part of the graph here? So essentially, with models such as Mamba, we have a higher control on optimization parameters. So essentially, as I was saying, Mamba is a sequence-to-sequence model where you're keeping this long-term memory and then you're looking into local patches of the image. In this version of Mamba, instead of looking into local information on patches of the image, we are looking into single pixels. Okay, so we are looking into a single pixel and comparing it to the long-term memory that we have. Okay, so we are predicting pixel-wise. We see how this actually is very inefficient, and even if we get results that in terms of veracity are comparable to UNet, it costs us much more. However, with Mamba, what we can do is, instead of looking into single pixels, we can look into windows, right? So now what we're looking is into a 4x4 window. I think this is what patch size 4 needs. We see how as soon as we change that, we get a model that is much more efficient, right? Because we have to compute way less steps. In terms of the flows, we are way below the UNet. And in terms of predicting capabilities, we are also way below. The last point is just computing the full training for the case when we have a patch size that is bigger, which is 8x8. And then we see that our results are comparable to the case of the patch size 4. So yeah, a couple images, just so that it is not only numbers what I'm showing you. These are some like predictions of ICL using UNet, attention UNet, and I think this is using the trans UNet. You can see how the attention UNet actually and surprisingly hallucinates and gives a more continuous distribution to the ICL fraction than the UNet. Yeah, and I think this is these two images are generated using the Dianoga dataset, and this is from the Illustrious 300. Okay, so we have a demo so that you can see it. I think you can show it, Martha.
Very short, but
Yeah.
I think it's worth it to show.
Well, we have implemented a dashboard, as you can see, in order to play a bit with the images. There are several parts. Here, we have some drop-downs to choose the features, input and output. Right now, we have just implemented the two, but as we mentioned before, we aim to implement more. As for the data sets, we are going to use Dianoga. And as for the models here, we have the checkpoints for fall. Once we select the data set, here we have a small viewer with the input feature and the output feature, and we can try to select and see how they look like. I didn't mention before, but this has been deployed with Docker, and I'm running it in local, but it can be deployed in any cluster. Also, you have to download the data. We are using local Dianoga. Once you have chosen the data set and the model, you can run the inference process. So this is just the predictions. Here, well, you have the output of the process, mainly about Hydra and the PyTorch Lightning pipeline. And then you have here the general metrics that Pablo was speaking about. This is for UNet. So we have 493 RASIP. The laws are the same ones than before. And you can also inspect the generated intra-cluster map. If we change the model, we can run the process again. And again, we have the predictions. As we can see, the results, they don't change too much. This may be influenced because we need more data. The ANOVA is quite small. And also we would need further hyperparameter tuning. But this is not an issue because we have the data and we are training the foundational model. And actually, this would be all. Not sure if you have any questions for us or something that you didn't understand.
I have a question. There was a slide on these different detection mechanisms.
Mhm.
Nice. Do they give like very different results between them? And like, is there a reason why you chose them? So I guess you've used the kinematic to the ground. Is there a reason why you've picked that method, that detection mechanism?
Well, this is something maybe Pablo will answer better, but this is something that this work has been already done by our colleague Ilaria, and we defined this case as interesting for this project. So we decided to go in that way, but we can explore other ways, of course.
Do they give like very different answers?
They do sometimes,
Yeah.
Especially in the separation region, the ICL and the PCD, there's no agreement between them. Not much agreement.
And is that because like the definition is different or the method is?
As far as I'm aware, there's different definitions. Yeah, like the method itself forces a definition of what ICL and BCD is. So, for example, the kinematic separation is just defining the ICL and the BCD sets of particles with different velocity distribution. Yeah.
Maybe I can add to that. I'm not an expert in that. But maybe, I think the other main difference is that the kinematic method relies on having all the information, and it only applies to the simulation. Right? The other methods are mainly applied to real data, where you don't have the 3D, phase space information, and you don't have the gravitational potential, right? So I guess what those methods are trying to approximate is the bottom. So the bottom one is sort of like the ground truth and quotations parts. I'm assuming.
Maybe I lost it somewhere. Thank you for a nice presentation. You said that in your presentation, there was like some part about the uncertainty quantification.
Yeah.
Then is it like
This
in the future or
it's something that we didn't consider right now. I mean, we can do it, but we didn't test it yet.
okay.
So the idea would be to try to include the loss of the random forest or the error margin, what we are missing, also in the model. Because maybe our prediction, the ECL prediction, as I mentioned before, the accuracy, let's say, is 65%.
So you work like a point estimate, and not the
Yeah.
is one or two like a confidence interval or
There will be confidences on the predictions depending on the pixel where you are. So probably in the regions that are on the boundary between where BCD dominates over ICL,
It's gonna be
you will
lower.
have higher uncertainty because for the random forest it's harder to approximate the ICL subpart. Yeah.
okay, yeah.
Yeah, and we want the network to be able to predict that as well. So in order to tell us how uncertain it is.
So it would be a way to see how sure you are about this prediction in this region of the map.
Always we point estimate that. Okay.
Yes.
Okay.
Yeah. Well, actually, what we are showing in the maps are the centers of the subhalos. So this is the most problematic region because it's where the ECL and the BCG are mixed. So it would be important to have this.
Yeah.
Mm.
Because maybe at that point you're not confident. You say also like this method you can translate to different simulations.
Yeah.
and maybe it works, but then you cannot like trust that one because you're not confident. You're working in the correct prediction, or like which regime are you working on? Maybe we can talk maybe later.
Yeah, but what did you?
I didn't get the point.
Because if you like not don't have like quantification of the confidence about the
Oh, yeah,
prediction, you're not
exactly.
you're
So
like applying this method. Like intrinsic problem of like
I know I 100% agree that this will be more applicable once we include the uncertainty estimations. For now, it's just trying to predict the ground truth as it is, just to see if the deep learning model is capable of learning the ICL sub 5. Now that's more or less what we want. And once we have seen that it's more or less able to learn it, then like even if I can provide you with uncertainty estimations, then you can be more certain that in this region you are probably certain that the answers from the model are mostly correct. Yeah.
It died just at the right point.
Yeah.
So that you can also, because different simulations give slightly different predictions, I guess, or you can split them, and then that gives you another source of uncertainty, right? The uncertainty due to the training set.
Would be like the noise of the simulation or the error.
It's
Simulation error.
Systematic, because different simulations have different. So when we were talking about yesterday, the subgrid models, this is sort of the devil in the details that can make very big differences for certain things. So like your galaxies can look very different, but what I'm guessing is that the ICL fraction is very robust to how you do the subgrid part, because it has to do with physics that is shared among the simulation. It has to do with gravity, which is done. It can be done sort of easily, correctly by all the simulations. So, but regardless, if there's any systematic there, if you train it on different sets and then you keep those models separate and then you make predictions and then you aggregate them, it sort of gives you like an approximate posterior on your prediction due to different simulations. So that's another interesting.
That's a good idea, actually. Yeah, we could try that.
Yeah,
for sure. Yeah.
Yeah, so then we are done.
Okay.
Thank you.
Well,
so we are going to go to the coffee break, and then we will have the Mare Nostrum visit. But we are done with the talks for today, so I think we can say goodbye to the people online until tomorrow. So yeah, and that's it. I hope you enjoyed the first day of the workshop, and I hope to see you tomorrow again. Okay, let's start. Welcome to the second day of our high performance computing visualization workshop organized by the Space COE in collaboration with Castiel 2 here at the Barcelona Supercomputing Center. I hope you enjoyed your visit to Mare Nostrum yesterday and our quantum computer. And today we have two sessions that are more focused than yesterday's on strictly data visualization. One will be an introduction to the theory of data visualization, very informal introduction, to give you a hint of what are the types of things that you have to consider or you can consider when visualizing data. And then we will have a hands-on workshop by IT that Peter and Milan will give. For performing visualization of complex and big data sets of coming from cosmological simulations in Blender, which is a VFX software that has a lot of potential for this kind of visualizations. So that's me. First, I'm going to say anything here. I work at the BSc in this group called the Data Analytics and Visualization Group. We are about 20 people now, working in the intersection of interaction, science, visualization, design, engineering. I am here in visualization and science, and I am the lead of the research line of scientific visualization and storytelling. I have a small team, and we work in developing appealing and informative visualizations, mostly for communication and dissemination. And these are some of the projects we've done over the years. And as you can see, we work in visualizations from many different domains. from medicine to computational fluid dynamics or earth systems. And also we are also involved sometimes in building interactive applications in the graphics part. But yeah, mostly in strictly visualization. This is a video we made some years ago about a tool to improve the predictions of seasonal to mid-seasonal predictions of weather and climate. Called Resilience, is online, and there is a bunch of maps in there. But we don't only do maps, we also do life sciences stuff. This is a tomorrow's cell growing, made by, it's a simulation, an agent-based simulation. These are molecular dynamics. So a lot of different things from very different domains. Sometimes we present the tools that we develop to visualize these things that sometimes don't exist. We cannot use pre-existing tools. We publish them and present them in posters or papers in conferences. And this is another film that we made a couple of years ago. Sometimes we submit our work to technical and scientific technical conferences like the supercomputing. We've also had some of our work featured in magazines and scientific journals like Science. And sometimes we help researchers do figures for their papers and research. So that's what we do. Now I'm going to show you a couple of charts, different ones, to make a point. So this is an old visualization. This is from the 1800s by Charles Minard. It's one of the first when the field was still information. And this is kind of the grandfather of a Sankey diagram. I don't know if you know, it's a kind of visualization that is very good to show flows because you can put intermediate like checkpoints and see how a quantity goes into one of the checkpoints and then splits into others to follow the flow of whatever you're visualizing. So here we are seeing the troops of Napoleon as they march towards Russia, trying to invade it. And we see how they failed in a very clear and raw way, right? So this number of troops, as they advance, you have, this is overimposed on the map. So you see all the geographical regions over here. And then you see how they go splitting as they march, but also how the size of the troops is reducing each time because this is winter and this is cold. And this is a century ago. So the conditions were very harsh with this. So when they reach and when they go back, so this is the way to Moscow and this is the retreat. Yeah. So yeah, it shows very clearly how the tragedy of the life loss as to how little people make it back home, right? You also have more information here as to on the temperature. So you can see that they reach like kind of minus 21 degrees Celsius. And you can establish some correlations as to, you know, more colder temperatures can have a greater effect on the on people basically dying of freezing or abandoning. And this is a modern one. This is a regular scatter plot made with the information. So they took books that have adaptations to film, right? And they took the score in IMDb for the movies and in Goodreads for the books. And they made this scatter plot with the two quantitative measurements on each of the axes, and they plot the correlation then. So it's nice. It's a kind of an exercise. It's good, made by 538, which is a media, very good one for data journalism. And because of the annotations, but also because of the nature of a scatter plot, you can clearly see some things like the trends and the patterns and outliers, right? So books that are very good movies, but poor books, and the other way around. So because of the annotations, you can also have a hint of where things stand. Whether some movies are also rated as good books, and the other way around. So what I'm going to talk about today is that what I showed you is data from IMDb, movies, books, but also molecules and maps and Napoleonic troops. And the thing is that it doesn't matter where the data come from, because the field of data visualization is about studying ways of developing frameworks that are independent of the provenance of the data, the nature of the data, in order to give us something that is more solid to analyze them in broader terms. So what I will try is that the main takeaway of this presentation is that you see that there is a same set of techniques that to produce any kind of visualization, independent of the whatever field you're working in and wherever the data comes from. Yeah. So, but why does this matter at all? So the thing is that it can be done wrong, right? Sometimes this is a chart from the financial newspaper here in Spain that says that the Central European Bank is maintaining the interest rate. And you see this line over here, the line chart. And usually I ask the audience, what do you see wrong here? But because I don't have much time, I'm just going to spoil it for you. I'm sorry. They are doing this, right? So the thing is, they want to stress the fact that they were raising a lot the interest rates, and then they stagnated because of whatever they want, whatever they want to make in the article. So they show you this sharp increase here, which is just not right. So it can be done by accident, this is someone who just got hired in the newspaper and don't know the software used to make the line charts or whatever. You can assume that it's not intentional. Also here, this is from a tweet from when it was tweeted by the former president of Colombia, Iván Duque, about collective homicides, right? So it's a bar chart that compares the victims and cases of collective murders between a period of time and another period of time. And says that here you have a big reduction in the number of both, right? But yeah, you saw that, right? So the thing is, this is kind of 4 times less than the other period. But here he's aggregating 8 years, and here it's 2. So that kind of makes sense. It's 4 times less, right? And also, what a coincidence! This coincides with when he was president, right? So again, you can be suspicious about the motives for this. And then we have the ultimate exaggeration of this. I don't know if you remember this, but in his presidential term, Donald Trump, there was the Hurricane Dorian arriving to the southeast coast of the US, and it was going to hit Florida, South Florida, and so on. And Donald Trump tweeted that it was going to hit Alabama as well, right? And he was very harsh on that. So the meteorological agencies of the US and some other state agencies hurried to say that it was not going to happen. Alabama was safe. So what Donald Trump did was to tweet, "I'm sorry, I was no, I'm kidding. He didn't do that. He just grabbed the map of the meteorological agency, a ballpen, a black ballpen, and drew a line over here on the top to say that he was right, that Alabama is going to be hit by the hurricane. So yeah, charts are very powerful means of communication because they speak directly to some of our visual perception cognitive mechanisms, and they can do this. One effect of that is that they can send the wrong information to us, and they can do this in much subtler ways than just drawing a black circle over whatever you want to stress in a map. This is a paper from 2006. I'm not an expert in this, so if there's any climate scientist here, please forgive me. But in this paper, they identified 2 ozone fields in the sharp contrasts of color of this map. So they have 2, one here between the dark blue and the greenish, and one here between the yellow and the green, right? So identify these 2. But the thing is that they plot this map using a very common extended preset of color in scientific visualization software, which is the rainbow color scale. Do you use it or have used it? And okay, so there are actually papers saying that this is harmful. Okay. So the thing is that if you plot this in a different color scheme, like a monochromatic scale, this boson field here kind of disappears or is not as strong as it was here. And this is because of a perceptual effect of us that yellow is perceived as brighter than the other colors. So, and the interpolation in the rainbow color scale is linear. So we perceive this band of yellow as more narrow than other colors like green or blue, for instance, right? So the variation in the values of your data is not translated as evenly in the variation in color of the color scale. So you see this sharp boundary here, which doesn't exist. It's a color perceptual mechanism. And even more subtle things like that can impede the correct legibility of a chart. But the good thing is that so these mechanisms can lie, but they can also help us in do better visualizations because some of these mechanisms are the same. This is a very nice example of a good visualization I like a lot because it's very clear and powerful. These are missless cases in the US. It's the rate, so it's one the cases number of cases by 100,000 inhabitants, and these are the 50. Don't remember. Sorry, is Canada already state? 50 states in the US, and you have each of the rows is each of the rows is state, and each of the columns is a year, right? So you see, because of this annotation, a very clear correlation between the introduction of the vaccine to measles and the almost not immediate, but very followed by the almost eradication of the disease, right? Also because of the color scale, what the color scale they chose, you can also see patterns in here, more subtle and less clear than this, but you can also see if you want to filter by state, so how some states have a greater prevalence of the disease than others. And maybe that correlates with, I don't know, weather or whatever. And this is another one. This type of visualization is called a tree map. It's a type of visualization that allows you to make a recursive clustering of information. This is an interactive visualization. It's online. I think I don't have the reference on that. Okay. I will put it in the handout of my slides. It's interactive and it allows you to inspect the stock market in the US. And the way in which this works is you have each box is a data point, so it's one value, one company, let's say, like Apple here. I think, yeah, Apple. The size of the box is the gross value of that company. The percentage here corresponds to the color, is the variation against one period of time. Let's say you can filter it the day before, 3 hours ago, a month ago, whatever. And then you have some recursive clustering. So you have consumer electronics here, which is Apple is the king, but not a good example. Here, software application, for instance, you have all these companies. Then they are clustered again on a higher level in the technology and so on. So you have a lot of information here, layered one on top of the other. You have like 3 or 4 categorical attributes for the grouping of the values. And then you have 3 quantitative attributes for the percentages, the gross value, and the different aggregations of that, right? So the size of this category also comes from the sum of all the companies inside. So a lot of information, but the beauty here is that it is very easy to extract information, right? To see patterns here. You can see immediately which sectors are not behaving as good or are not as good as others, for instance. You can see immediately spot outliers, right? Things that are not working among others that are in the same sector and things like that. So charts can also tell the truth. And the reason, so simplifying a lot, the reason is because we are much better at extracting information from this than from this, right? That this is something complex. It's take a lot, for instance, to learn how to write language and numbers. But this speaks directly to some things that happen in our brains, in our minds, that are faster sometimes, right? And also we are kind of good with graphics. So if we want to, I don't know, answer some very simple questions about the kind of small data set, only a few rows and columns, it would take a lot of effort, if not time, at least, right? What if we do it here? It's just very clear with the world average, with the country with the highest and lowest life expectancy at birth, and so on. So let's go with a definition. One definition of data visualization is that it is the visual representation of complex information in a way that aids reasoning and comprehension. And here it is implicit that it aids someone, a human user. Which means that data visualization are tools to help us think. And because of that, they can also make us think in the wrong direction, right? Like the charts I showed you before. And this is called external representations, the idea that we use things that are external to us to help us do something to overcome limitations of our cognitive system, of how we perceive things. So in the same way as you can see a book or a notebook as an external hard drive for our memory, things that we cannot remember very good, we can put it there to remember later. You can see data visualizations as cognitive tools to help us think and reason about something, right? And there is a lot of research. This is an active field of research and a very interesting one that researchers into how we perceive visually things and how can we apply this knowledge to making better visualization, right? So there are two main authors I put here, Colin Ware. This is a very comprehensive book with a lot of experimental studies about this, where they not only perform cognitive sciences studies, but also they show people different visualizations and they ask them to perform different tasks in order to evaluate the efficiency and how fast they can perform those tasks and so on, and try to make rankings of visualizations in those terms and things like that. And this one is a more introductory one, Jen Johnson, Designing with the Mind in Mind, but also very good about this topic. So to show you how this works, do you see the white triangle here? Yeah, and do you see the black line, the triangle with the, okay. I am sorry for breaking this to you, but there are no white triangles and no black triangles. So there are three Pac-Mans here looking to each other, and there is some angles here also facing each other. So what happens is that we don't see the world as it is, right? There's a lot of processing happening in between what we acquire in our mind and what we see with our eyes. Do you know this one? No? Okay, what do you see here? Okay. Wow, who did? You? But you've already seen it. Ah, okay, cool. That's the fastest answer I get so far. Yes, okay, good group. Okay, so it is a Dalmatian dog. It is sniffing the ground. Here is the head. Here are the legs, and this is the butt, let's say. This is kind of a tree, the shadow of the tree. It's in a park, walking like this. Yeah? You see it? Yeah. So the magic of this is not only seeing it, which it can be more or less difficult. The good thing is that if you ever see this again, you cannot unsee the dog, right? Now there is meaning imposed over this image. So you cannot forget that there is a dog here. You will always see the dog. And these kind of things that play against us if we don't use it, with consciously, but they can also help us. So what do you imagine could be that if a user has to perform a task here, right, in this visualization, the task will be find the red dot, right? Because it's something you don't even have to think. There are some of these cognitive mechanisms that we are tuned to detect some things very easy and very fast. Like, for instance, color contrast. Two colors that are very different to each other, we are very good at spotting the difference. That is why this works here. Oh, Miran Jaros. Now? Okay. How do I will do it later. Yeah.
Yes, sure.
Okay. So yeah, and there are other mechanisms like this that also play an important role in visualization. Like, for instance, we are very good at spotting small differences in height in objects that are close together. That's why bar charts are kind of the most at the top in the list of the most effective kind of visualizations, because we can even spot difference like this, right? So to make subtle comparisons, they are very useful. So how can we apply this to visualization? There is a very useful framework proposed by Tamara Monster, a researcher in data visualization and professor, which is this one. That again, taking our definition of it's kind of an evolution of it. So it's visual representations of complex information that help someone, a human user, perform a task, right? And she proposes this feedback loop in which you have the data, you do something with the data to prepare it to be visualized. And then you have, this is kind of the central process of it, which is visual encoding. That means it's the process of transforming your data into graphical elements, right? So a mapping. And then this goes into the human user that is required to perform some specific task or tasks, and it can serve to inform your visual encoding and refine and iterate over them. Yeah. So this is a basic process of data visualization that serves as a framework for analyzing visualizations, but also for producing them, and has the advantage that it's general enough. It's kind of they call it a grammar, because it's general enough to data from all types of domains. The human user is important because a visualization is, as I said, a cognitive tool that exploits human capabilities, right? So if there is no human to exploit, it's not necessarily the best solution. So visualization is, it will be necessary, or it is we build visualizations if we don't have something that goes faster than us, right? So if you have an algorithm or you can develop an algorithm in a time that is more reduced than what it would take you to build a visualization, then obviously there might be another solution. But if you want, so visualizations, because we have a lot of tools now to make visualization, can be a very fast and easy way to make at least first visual exploratory analysis of what you have. So visualizations are good when we don't know the questions we want to ask in advance. So to do this kind of fast explorations of what you have of your data, they can be very, very useful, and also less costly than developing algorithms sometimes. So again, having we make visualizations only when we need them, when we want to exploit human capabilities of pattern recognition and so on. Because visualizations exploit this perceptual and cognitive mechanism, right? We're good at spotting contrast. We are good at making accurate judgments of length. We are good at seeing some stuff that are behind the reason why visualizations are a suitable tool for exploring data. So an example, but sorry, yes. So visual encoding, this is tricky, and I am not going to have time to go to be very detailed about this because it's long, but I will give you just a hint of how this works. Visual encoding is about putting in your data, transform your data into visual graphical things, right? Which are called marks. But these marks and the visual channels that modulate its appearance, like color or position or height or whatever, are not all equal. Okay, so what would you say in this chart goes in the x-axis? If I show you this, prices, what else can be? Definitely can be prices. So, these are car models, right? The Bill, the Honda Accord. Horsepower. Perfect. It could be horsepower, yes.
Number of cars sold 1 year.
Number of cars sold in a year, exactly. So, no, it's marking the intersection with the country where it was manufactured, right? So the Honda Accord is made in Japan. The Dasher was made in Germany. Yes. So why would you think that this was a quantitative measure? Because they are using parts, they are using length, size, and size speaks to us in terms of how much. It's a quantitative, it's magnitude channel. Yes, it's over here. So there are some kinds of marks that speak to us in these terms, and there are some others like color hue or spatial region or shape that speak to us in terms of identity, right? So what is this and how much is this? Kind of reducing a lot, okay? So it does matter because if you don't use this, let's say with an intention, you can end up with this, right? With sending the wrong message. And this is the opposite effect. This is a chart, it's a fake chart for of the average height in inches of female and male students in a classroom. Okay, so you have females and males here, and you have the average height. So it makes sense to visualize this in a bar chart because you have two different categories. So if you use a spatial position, this, to separate the categories and also different color hues, you transmit the idea clearly that you are dealing with two separate things, two identities, two categories. If you do the same chart with a line chart, then you are sending the message to your audience that there is an implicit relation between them, right? There is maybe a quantitative relation where there isn't. Okay, so again, it is important to keep in mind that channels are different in nature. And they are also more or less effective in terms of how we perceive them. This is the Stevens law from the 57th. It's from a field of psychology called psychophysics that deals with the relationship between physical stimuli and our sensory response, right? So this is the results of an experimental study that they performed where the cohort of participants was exposed to a series of stimuli, normal stimuli like the brightness of a light, for instance, and then they had to assess the intensity, right? So they had a baseline, and then they doubled the intensity or they increased the intensity of the stimuli, and they were again asked to assess how much was it increased. So, for instance, for brightness of a light, it's the baseline 1.1. But when the light is doubled, the perception is not doubled. It's the gray line. It's not here. And this, as it increases, it also tends to go down. And this makes sense because our eyes are good at adapting to different light conditions, right? We don't want to go blind when there is a lot of sun or snow or whatever. So our eyes adapt to different brightness conditions, then tending to minimize the effect of brightness. This happens for depth and area. For length, interestingly, when the participants were shown a line of length and then another one of double the size, they were very, very accurate at responding that it was bigger and how much bigger. And this might be behind why bar charts are so effective in this type, because we are very good at making this type of comparisons. On the other side, we also tend to, let's say, exaggerate or over perceive some stimuli, like saturation of color, but also electric shock. This is not a battery car with jumper cables. This was only an electrode on the finger, I think, something like that. But when the intensity of this electric shock was doubled, the perceived uncomfortability of the subjects was like, oh my God, this is 5 or 10 or whatever times stronger than it really were. So we tend to we don't perceive everything as in an equal manner, right? And this is helpful for us because it can be extrapolated to how we design visualizations. This is an example of how 5 quantities can be plotted in different ways, and you can see which ones you can make better judgments or more accurate judgments, right? So lines are at the top of this type of charts because what I said. Then you have position of points, which are also good, but starting, so this is a top to bottom thing, right? So these are better, these are a bit less better. Areas we are not very good, but in some cases it can be good when we are not concerned about this accurate comparisons, but whole pattern thing. For areas and angles, then it gets tricky because for some cases they are good, and in some others not. And there is a lot of work also validating these things. So there are like crowdsourcing experiments on the internet where people is asked to use visualizations and the results of the time response, how fast they perform the task, and the assessment of how easy it was to use it. So user experience and usability of charts go to help us build this ranking of effective visualizations. Which ones are better and which ones are worse. And then we also have, so this is the separation of the basic elements that we can use to build visualizations that are separated into the magnitude and the identity channels, but they are also ranked from more effective to less effective. Thanks to these experimental studies and other types of studies to assess how effective they are, right? So at the top, we have position, and then we have volume at the bottom, and some others in between. So how am I doing? Okay, we stay. So how do we apply this to what you do? So I'm going to give you 3 hints because I am running out of time. Very quick ones that might serve you, okay? I assume that you are not ever going to do something like this in your job. And you will probably not do something like this. It's a pie chart in 3D. A pie chart is, okay. But in 3D is even worse. If you have hundreds of categories, it's layers of making it worse and worse.
Are we worse on volumes than areas?
Sorry?
Are we worse on our volumes than areas? Is it worse with volumes than areas perceived?
Okay, so volumes are 3D stuff. It's complicated because there are some things we do to compensate. So if you have you seen this the trick of picking the pyramid of the Taj Mahal?
Yeah.
That is a compensation effect that we apply, right? So if you have a bar chart in 3D with a perspective, you are distorting the size of the bar. So you are diminishing the ability of people to make accurate judgments. But there are some things, I mean, most of the work I do is 3D. So there are some things that are inherently 3D and you cannot get away with that. So there are also strategies to cope with that, like avoiding cluttering or use transparency or adding scales or whatever. Yeah.
So did you say that pie charts are always bad?
No, I didn't. I did? No. But I said they are complicated because they are based on angles. So they have to be handled with care, extreme care. I have a presentation of about pie charts, but I'm not going to do it today. No, this might be more useful for you. So axis, when do you want to, this is an unemployment rate. Yeah, unemployment number. In Spain, this is from the national TV, and surprise, this is kind of the Colombian president one. This coincides with the president of the moment. So he said, oh, the unemployment was, it's nearly nothing, right? But it's not. So because there is no zero baseline here, the axis. Here you have it, right? So in theory, you could say that in line charts you want to have your complete axis, but sometimes you don't. So for some charts, you might want to see the subtle variations in something, right? So a general rule of thumb is that line charts are basically dot charts, and there are points, right? That discrete measures so where you place your data, and then you link that with a line to make it easier to read. Because they are point position, it is okay to not show the whole the whole axis from 0 to whatever it is. Only keep in mind that whether you choose to flatten it up or to stretch it up, you are stressing different things. You are either showing a trend or variations or whatever other feature in the data. But when you are playing with bars, it's different because bars are encoded in the size of the bar, the size of the line. And if you cut the size, then you are immediately just distorting the values, right? What is actually your data. So as a general rule of thumb, this is okay here, but never in bars. And never with percentages. Another one is, so this kind of a reminder. It's not really a trick but it might be useful as a reminder as well to remember to add annotation. So this happens a lot in scientific environments that you tend to think, because it's what you do, that everyone has the same level of understanding, or at least very similar or close to what you have. And it's not true. People doesn't know what you're talking about if you don't help them. So adding labels, annotations, and things that make your charts or graphs or visualizations clearer to your audience is always a good idea. Don't assume that they know what you're showing, but tell them. And this not only goes into the legends and the labels, but also in the choice of colors, right? So at this point, the last one was about box plots and the importance of showing the whole distribution of your data. But I thought that because I saw a lot of videos and images in color in the presentations yesterday, that it might be more useful for you to discuss color. But I don't have time for both. What do we do? Color? Color. Okay. Color, when we say color, we are usually talking about three different things: luminance, saturation, and hue. And this is one way of understanding color. There are other models for color, but this is useful in terms of visualization because these are perceived, again, as magnitude channels. So we can use luminance and saturation to encode quantitative information. And we can use hue because we perceive it that way as an identity channel to separate things, right? So this is a useful categorization of color in terms of visualization. And in color happens something similar to what I showed you with the Dalmatian. Our eyes can play tricks on us, and color is complicated in that regard. So if I tell you that this color and this color are the same, do you believe me? Yeah, because I haven't given you any reason not to trust me. But they don't look the same, right? Not at all. But they are. And this is an effect called simultaneous contrast, that again happens because we modulate how we perceive color and light in terms of what surrounds color, right? This is the same effect as you remember the blue or gold dress. Yeah, so it's the same thing. It depends on what is around what you're looking. It changes to us, of course. So, and this is the reason why this doesn't work, right? Because we don't perceive the rainbow color scale was designed in a time where we thought that we processed light it was designed for machines. Okay, it uses a color model that is how computers process color, RGB, and so on. And the interpolation between colors is linear, and it doesn't match the way in which we process color. So luckily, this for some years now, There is a lot of work into this, and most visualization softwares have what are called perceptually correct linear scales, which are designed in the way, and also they use color spaces that match the way in which we perceive color. These color spaces are not RGB, can be HSL. I don't know if that sounds like something, no? Okay. Different ways of interpolating color, light. And the basic idea behind here, well, there are two basic ideas. One is that the way in which the color varies along the scale is even as possible, in order to reflect the even variation of your data. Okay. The other thing is that it's accessible, so it can be understood or read by people with color, some type of color efficiency, like Protanope or Deuteranope or something like that. But also they also think about people who still print papers in black and white. So most of these color scales might also work in if you completely desaturate them. Yeah, sure.
I often have the problem that I want to show a lot of subtle variations in the data, and the perceptually uniform ones don't have so much variation. So it's better with the.
I know, no. So perceptually correct doesn't mean it's monochromatic. It just means that the interpolation between the colors is even. So you can have something like the magma color scale, the viridis, that have like 4 or 5 different colors.
Yeah, but it's still not as many as the rainbow. If you want.
And you also have a perceptually correct rainbow, which corrects the lightness and the saturation of each of the data of the color points to make the interpolation smooth. So there is, if you want to use the rainbow, you still, because there is now a version of.
Does Matplotlib have?
I don't know. I didn't use Matplotlib, but surely it has, because I don't know if I took the. Yeah, sorry, I don't have that slide anymore. There are a lot of libraries for this in both visualization tools, like in R, in surely Matplotlib has, and in Python. You also have filters, like to test your color scale before releasing it for most of these effects. And yeah, one quick thing about how to use color in visualization, how to map data into color. We have 3 main kinds of color scales: categorical ones, sequential, and divergent. These two are essentially the same. They only differ in that this one is used when you have your data increasing from one value until another, and divergent is when you have a middle point that you want. Just like in temperature, you have 0, minus, plus, whatever. So yeah, quantitative is just straightforward. You have something that goes from one point to another, and you map it. You can discretize it, and you are familiar with this. With the divergent ones, the only thing you have to take into consideration is to match the middle point in your data with the middle point in your color, which is also easy. And with categorical, there is this rule of thumb that beyond 12 colors, more or less, you start repeating colors. So it starts becoming more and more difficult to tell apart in the visualization, not necessarily in the color scale, but in the visualization, what corresponds to what. And it takes more, let's say, cognitive effort for your audience to go back and forth to the legend to see exactly what color you're representing in what. So, and our friend the pie chart doesn't cope well with a lot of categories neither. And one other last aspect of color is that color has a meaning, a cultural meaning. So there is some semantics of color. It's a fantastic infographic of the China morning. Oh, Chinese newspaper. I'm sorry, I forgot the name, and it's just under my label over here. So you have the reference down there. It's a visualization of the human cost of the Iraq invasion, right? So it's a bar chart, essentially, a stacked bar chart. You have one set of bars over here with the casualties, with the deaths of the coalition, forces, and then you have another one with the Iraq civil deaths, right? But it's a bar chart that is inverted, it's in bright red, so it's blood dripping to stress the message of the tragedy of this. But the story would have been very, very different if you do something like this, right? So if you just put a regular bar chart and you put like a greenish happy color, then the message is completely different. So it depends. You can also use color not only for clarity, which is obviously the main concern, but you can also use it to match whatever you are trying to convey. For instance, if you're working with temperature or you're working, there are already color schemes that are called temperature, hot, cold, or black body, or whatever, that are very, let's say, descriptive. But you can also account for this, right? If you're plotting ocean data, you can use blues. If you're using solar radiation, you can use something in the yellowish and so on. Some things to consider is assign color to meaning. Use the correct scale for each attribute, depending on if it's categorical or quantitative or divergent or sequential. One thing that we usually overlook is that in this example, for instance, it's a data set of vegetation, right? Or CO2, I don't remember, but it's only in the air, in land surface. So there's no data for the ocean, but the color chosen for where there is no data for the ocean is very similar to what to the lowest color in the color scale, so the one in the desert. So this might lead the audience to think that this is actually representing data when it's not. So a good practice is to use no color for no data, like a gray or a neutral thing that is very different to what you're using to plot your data. And yeah, the ecosystem of visualizations is very, very, very rich. This is quite old, it's from 2010, but it already gives you an idea of some unconventional visualizations at the time that are becoming more and more popular, other than line charted scatter plots and things like that, like string graphs, variations of string graphs, and a lot of things. And they are also permeating a lot into other fields like journalism, for instance, that is using more and more visualizations. And yeah, so with this I finish. I hope you hint on what I was trying to do, which is conveying this idea that the field of data visualization deals with giving us a framework in which to analyze and produce visualizations that is independent of wherever the data comes from. Yes, there's a lot of bibliography here if you are interested in this. These are my two reference books. Tamara Mosnet is the one that proposed this framework that I showed you, the feedback loop of data visualization design. Functional art is more, let's say, light read, but also very interesting. And you have others. Thank you. Questions?
Can you go back between so in our field, I would say, or at least in my field, we use a lot of line plots, right? Lines connecting things.
Okay.
Because usually it's something that is varying continuously, right? So there's no discrete categories. Yeah, exactly. Because you actually assume that between the 2 points, there's actually a variation that is close to that line, right? Even if it's not real. Although sometimes you put the points on top of the thing to show the error bars or to show where the actual data is and where you're actually interpolating, right?
Correct.
But you were saying that sometimes the bar chart is more informative.
No, but they are meant for different things. Bar charts are for when you want to compare two different things, And I mean, you can compare two different things in a line chart if you have two lines, right? And you can compare, but it's they are mostly used for evolution over time or over and whereas bars are not as good for that.
So if you don't have any connection between the different objects or categories on the x-axis, then you shouldn't use. It's better to use a bar chart then.
I would say so, yeah, but it also depends a lot on the specific thing.
Yeah, maybe I can show you later.
Yeah, sure. Yes, very important to make accessible visualizations. Okay. Finish. I'm going to make Milan a co-host, and then we continue with Blender.
Okay, so hello everyone. My name is Petr Strakos, and together with my colleague Milan Jaroš, we work within Space Project on interactive volume-based cinematic visualization. That's how we call it. And mainly we use Blender for the thing. And yeah, because this workshop or our part of the workshop is meant as a hands-on, so mainly in Blender. But before we go to this, I want to kind of introduce the topic and mainly our work within the space project. And then we will directly jump to Blender and try some bits of those things that we are trying to develop within the space project. But obviously, since it's being streamed and remote, so with much smaller scale than we work on within the space project. So apologize for those who already heard or see this presentation during our meeting. But yeah, I am gonna use it to introduce those that are new today. So to introduce you into the topic. Since astrophysical and cosmological simulation codes generate quite a huge amount of data, so it needs also some efficient visualization tools to extract the insights. And in our work, we decided to go along with volume rendering, since it is capable of visualizing the entire simulation domain at once, and especially in VFX tools such as Blender, it can be visualized very nicely, let's say, in high level of detail. So yeah, this is the way we decided to go and stuff we are working on right now. And in our case, we work on high performance, scalable visualization workflow that leverages not only Blender as itself, but also powerful cycles renderer that is part of a Blender. And we also have been working on modified version of cycles renderer, which I will mention later, that we use in this work. So we are trying to convert large-scale simulation data into volumetric format. We support interactive real-time visualization while using path tracing, which is the main rendering concept of cycles. And yeah, with such, we are able to provide user with sufficient tool to set up their visualization and then enable high quality offline rendering to reaching final outputs. And for this, we are developing several add-ons for Blender that allow all of this stuff. So as for the tools, here is the overview of the tools we are developing. One of them, or the first one, is we call it vSpace add-on. Basically, it integrates or provides user interface within Blender. and allows user to interact with the data through another tool, which we call the Space Converter. And this tool is capable or able to load the data from disk to CPU memory, perform the voxelization, and basically the conversion to volumetric format. We are using VDB format that is natively supported in Blender, and the converter then sends data from server to renderer, and depending whether we are using remote or local renderer, it's the rendering happens either there or there. So yeah, that's for the renderer. On the right-hand side, you can see some examples of how it can look like and what is behind our concept. So since the input data are quite huge, so our approach is to basically provide several levels of visualizing the data through volumetric format. So in the topmost image, you can see 3 levels. So in the first one, you are seeing the whole data set, and then you are able to focus on some smaller details within the data set and transition from one to another level triggers another conversion to volumetric format and visualize the output for the user. And at the bottom, you can see some examples of visualizations from Open Gadget dataset. This is one of the codes that is being developed within the space project, and we are able to use and visualize its outputs. As for the BSpace add-on, because this is the main one through the user can interact with the data. So basically what you are seeing now is kind of standard Blender interface with the view editor where you observe your data. In this example, we have used Jenga dataset, so data from another code that is being developed within the space project after converting it to volumetric format. Within this visualization already the cycles render is being applied, so the visual output is being path traced. And here is the, let's say, main part of the add-on through which the user can interact with the data. So it is possible to select what kind of data the user wants to provide through the conversion and so on. And at the bottom part, there is a shader editor, which is standard editor in Blender, where you can set up visual output or how the data will be visualized by applying specific set of shader nodes to provide the final output. In our approach, we are developing, let's say, 2 main branches. One is, we call it local rendering one, and the other one is remote rendering. So as for the local rendering, what we are seeing in the first part, there is a part that runs on the cluster. That's the space converter part, within which we can access the data, load them in the memory using multiple set of nodes, perform the voxelization, and store the results as a converted output into standard format. Either it can be NanoVDB or OpenVDB that is supported in Blender. This kind of output is then being imported, transferred through TCP to your local computer, where it is directly imported into Blender. and visualized using cycles renderer. So that's the local rendering part. And because the size of the data can be very large and will be very, very large, so mainly for these reasons, we are also working on a remote rendering part. So also the rendering happens on the cluster. So the space converter part, so the conversion of the data to volumetric format is basically the same. Here we strictly focus on just the nano-VDB format because this kind of format is basically optimized for GPU rendering. So we are using this. And as for the rendering, here you can already see our modified version of Cycles renderer, which we call Cycles 5. And this version of renderer supports basically the interaction between the space converter that provides the data and local instance of a blender that basically sends the setup for the shader and for the scene, let's say. So this way we are able to basically allocate and use more resources for rendering, and we send just the rendered image that corresponds with the view through the camera to local instance of a blender. And here are some scaling results which we have tried so far. So those were done on Carolina cluster that is located at IT for Innovations. For this test, we used 64 CPU nodes, and it was a data set from Jenga code, and that contained 12 billion particles. And basically, what you can see in the chart is that we performed the loading and the conversion into volumetric format, and as we have been adding more nodes and also MPI processes, the scaling performs as expected. The subtle lag at the end is caused basically by the I/O. So too many processes were accessing a single file, but the possible solution might be splitting the file over multiple I/O resources. Here are some visualization results. So we took again data from Chang'e that represent single high-resolution non-cosmological isolated galaxy, I hope. And applied our toolset through Blender. And on the left-hand side, you can see a standard tool that is very often used. It is a tool called Splash for visualizing such results, and on the right-hand side, the results from Blender. Here are some future steps. So mainly we want to focus on expanding the data support, improve voxelization, optimize data pipeline, and which is very important, introduce animation workflows. And here is a short example. Basically the interaction through vSpace add-on with the space converter. So here we are starting the space converter as a server, and from Blender we connect to that and ask for doing the conversion and sending the data. So on those data, we directly apply some preset shader, and we are able to visualize the data, and then in kind of standard way, play with the data, set the shader details and so on. So basically prepare the whole scene for final visualization using rendering. Okay, so that's as the introduction to the topic. So that was the presentation, and now I would like to switch to Blender. Yeah. All of you should get the link to already prepared data for this part of course. So either you were able to download it, or you can try to do it right now, or you can just watch and listen and download it later. We tried to prepare it with Milan the way that even though it's hands-on, you can do the hands-on even also later. Yeah, so it depends on your preference. So yeah, here is the link to the data. Probably it's not necessary to copy it to the chat. So are you all set? Can I continue? Probably yes. Pardon me?
Where's the link?
It's in the chat of the Zoom meeting.
So I have to log in first.
They're also in the email. I think there was an email.
Yeah. It is in chat, so you can copy it directly from there.
Well, we're doing that. Just a question,
Mhm.
the video you showed. So the interaction, was it streamed from HPC cluster, the rendered images, or was the visualization?
No, that was
locally?
the local version. So basically, we did just the conversion on a cluster and then shipped the volumetric data in the volumetric format to local
What's
instance.
the resolution of that? Because the interactivity was really good.
I will show it in the example because we have exactly the same data.
Sorry, I didn't file.
Yeah, but typically we work with something like 300 times 300 times 300 number of voxels, so something like that. Yeah.
Following on that, you have examples of CFD simulations, which are also very, very big, of computational fluid dynamics running in the cluster with a fairly good interactivity as well, right?
Yeah. I can maybe point you later. We have a web page with specifically this topic where we visualize CFD data, basically using the same concept. Yeah, so our aim is to make it general enough, even though this is space domain, but simply general enough so we can work with more kind of data in volumetric format. Okay, so
Somebody was asking a question.
yeah, and as for maybe some kind of organization, because Milan, my colleague, is remotely connected, so he will mainly focus on answering the question. But yeah, I can also try to do this. Yeah, so there is a question whether it is possible to apply or use our tool in VR. Basically, it is possible in some extent because in Blender, so let me start Blender. If you want to follow, the best way would be if you have already the data. So to basically go to the directory with the data, which I have right here. So if I go back to the repository, so basically I clone the repository as well. And in that folder, there is the whole structure or all set of data we will be playing with right now. So yeah, if you go to this folder, within the data and start Blender, because I will be running some scripts. So basically just the meaning is just to be or have that folder as a current folder within the Blender environment. So I have started the Blender, and just to answer, let's say kind of quickly, the possibility to to use VR. Blender natively supports, they call it VR inspection. And I haven't used it for a while, but it should be, if you open preferences, I remember shortcut. Yeah, here. So it's under the edit and preferences. So there is a section of add-ons. And there is, by default, it's not turned on, but there is an add-on provided by Blender team. It's called VR inspection, VR scene inspection, and through this add-on, you are able to connect typical VR headsets, typically those game headsets, and you can inspect the scene through the VR headset. So basically, you are able to see the content of the scene provided through this kind of editor, which is 3D viewport. It supports surface geometry, so not every stuff is being visualized. And as for the volumes, because it uses just some of the renderers that are provided in Blender, so you will be kind of limited. But yeah, some kind of VR inspection through VR headset is possible in Blender, let's say by default. Okay, so here we are in Blender. I would just do some quick overview in the Blender environment. So I started the Blender, and in its default setup, it should open for you like this. So basically, you are provided with the main 3D viewport view, and all of those windows or portions, parts of the window within the Blender environment you can see are basically different kinds of editors, and you can always find switch knob in upper left corner, and you can select different one. Yeah, so here is the whole list of different editors. And since Blender is quite versatile and can be used for lots of stuff, so yeah, that's why also there is quite a lot of editors. And we will mainly focus on using 3D viewport and geometry node editor, shader editor, and the text editor if we want to run some scripts. Regarding the Blender environment, there are also some already prepared presets for you as a user, so you don't have to manage the layout. So for example, by default, you open Blender in this layout, but there are different layouts as well, so you can just try to switch between them. So I mentioned geometry nodes. So for example, yeah, nice already prepared layout for this is called geometry nodes. For some development and testing, there is a script layout. So basically in this layout, yeah, so you are being viewed, or you can view the text editor through which you can, or where you can type your piece of code that you can then run through Blender, because Blender is equipped with Python console, which you can see here. So it is able to run Python codes, which we will also experience. So yeah, different layouts for different type of work. You can also create your own. If you move your cursor over, let's say, corners of one or another specific editor, you are then able to set up, for example, if I want to split this, so I can go to that right top corner and split it in half, let's say, and have another editor if I wish, and then select the one I need. And if you want to get rid of that with using right mouse button, you are able to close the editor, which is, let me see. Yeah, close the area.
Is the Python console running locally or remotely?
It's running locally. Blender is built with the Python version, and if I, for example, switch to scripting layout to have a Python console, so you can see the version of the Python that is built with Blender. And maybe another important thing is to show you possibility of adding add-ons and kind of setting up the layout. So in the preferences, there is a possibility to kind of adapt the layout to your needs. For example, here you can see that there is a tuning knob called resolution scale. So you can basically change the scale of fonts to better see. I don't know, for this purpose, maybe this is great one or the good one. You can also turn on several other stuff, and especially if you are developing some tools, there are, for example, developer extras and Python tooltips, meaning that you can get some kind of help or reference if you hover over some tunable parameter in Blender environment. So, for example, here you can see basically the Python tooltip that you can also copy. Yeah, by copying full data path. So you are then able to access this kind of stuff and then copy it in the console, and you can get the value back. So this way you can start learning how you can influence and how you can control some stuff in Blender directly. So this is kind of helpful. And if I go back to preferences, yeah, one important one is hidden in a system or located in a system, and depending on the machine you are running Blender on, it can provide you quite a significant boost, especially when you do some rendering experiments. So, for example, I'm on Apple machine, and I have a Blender version of Blender that supports metal hardware, so Apple hardware, and especially for rendering, you can turn it on, so it's being used for the rendering. similar depending on your hardware and system version. You can turn some additional support from the respective hardware to help in the rendering. In Blender, there's also part in the preferences through which you can try to search for already existing tools that can make it easier for you in almost whatever area you are trying to do some kind of data processing connected with visualization. So yeah, there is a get extension ability, so we can try to search for some extension that could be then installed into Blender, and you will be able then access it through the Blender environment. This should be let's say officially serviced by Blender, so new stuff can appear here. Opposed to this, those ones should be already made part of Blender when you install Blender, or you have installed it by yourself by simply installing the add-on. So yeah, you can install either your own add-on through this option, or when you download someone else add-on, so you can install it this way into Blender environment, and then by ticking it, use it. Yeah? So for example, here we have our add-on that we use for rendering. Basically, yeah, this offers the user ability to offload your prepared scene for final rendering to cluster, and then render the output on the cluster, and then being able to get back the results of it. But yeah, there is plenty of other add-ons depending on your needs. So either you can find it in here, or you can install it from disk if you find it somewhere on the internet, or you can try it even through here and go through the library of existing add-ons that are being supported by Blender. Yeah.
If I wanted to run the server on a cluster, I have to install some plugin or something.
In this hands-on, we, let's say, will be showing just smaller subsets of those tools that we then have created the thing I was describing during the presentation. So through this hands-on, we won't connect to any server, but the main message I would like to pass is that even though we, let's say, won't be using any specific add-on right now, you already have quite a lot of stuff to visualize your data. And then if you would need to go more on scale, yeah, either our tools will be made available after or through the project, or yeah, we can get in contact and we can help you with that.
Okay.
If you
So
have
just
some.
for curiosity, you developed the tool for integrating with the HPC clusters.
Yeah. So for example, the add-on I mentioned in here, this is our add-on, and as soon as you have an account on a cluster, for example, here you can see some kind of setup for that. So if you have access to the cluster, here I have access to Carolina and Lumi cluster. I'm then able to remotely basically connect to those and offload my work I prepare locally on my computer, and then let it render on a cluster, and then just download the results back. Okay, so yeah, this is very quick overview to Blender environment. And before we let's say start dealing with the data that I have provided with my colleague, maybe it would be good to first describe what we have provided. I will be using Visual Studio Code just to, in more easy way, show you what is the content of those data generating scripts, and what was the main purpose, and then we will go back to Blender and directly open the data and work with the data. So for basically this hands-on, we decided to do small simulation. Basically, it's a demonstration of Newton's law. So we have two mass objects that basically interact between each other using gravitational law. So in that script, we have some kind of setup for that scenario. We have two objects with some masses, and we set the gravitational constant. And because we will be also showing the voxelization approach, so we also have set some smoothing length parameters for those two objects that in that respect are represented as particles. We set up them with some initial positions, and we basically simulated through several number of steps, specifically 1,200 steps. And we store the results for each individual step, and those results will be then loaded using Blender, and we will continue our visualization on this kind of data. So just to have an idea, so if I run it in here, so basically that's the animation of those two massive objects. One is lighter than the other. So the lighter one obviously moves faster than the heavier one. And we selected some specific setup in order to achieve this kind of animation and influencing one object by the other. So the data were then saved as basically NumPy arrays with such a structure that is shown in here. So what we are saving is, let's say, the frame number, the position of each particle at that step or at that respective frame, its velocity, its mass, and the SPH parameter that we will then use later. So this has been stored in those two files, each file for each particle. Basically, you don't have to run the script because the data are already in there, in here specifically. So just to have an idea what are the data about. And if I then go to another Python script for which we can open already one of the scenes. Called load npz.blend file. So basically, in that scene, you can see that we already have those particles that I was speaking about. And specifically, we have their, let's say, trajectories. We also have in the script editor, we have opened the Blender load npz.py file. So in case you would like to do some changes on it, you can do it directly. So you can basically run the script. And if I do this, it should basically load again the particle data from those two files and create sorry, create respective mesh, which you can see in here. And basically, we are using one of typical objects from Blender mesh to hold the data that we were talking about in here. So basically, it should contain this, or respectively, we are then transferring it to to this description. So if I try to comment a bit this script that then provides this output. So we load the files and we call this function that creates a new mesh object in Blender. And within that, it uses the data loaded from those NumPy arrays to set the attributes of each individual mesh, while each mesh is individual particle with specific names. And those names can be seen in here. Another kind of editor, which is very convenient to explore the data you are dealing with in case you want to apply some kind of additional processing over this data. So yeah, for example, here I have selected particle 1 mesh. So within that mesh, we have loaded or created these attributes such as position, mass, SPH, frame, and velocity. And those parameters will then be used to basically create the animation, something you have seen before when I started the script and showed that simple animation in Matplot. So we will try to replicate this in Blender and enhance it with some additional stuff using geometry nodes and also adding volumetric objects that will be voxelized using the techniques that we are actually using also within the space project. So yeah, those are those small bits of what I have presented in the presentation, but represented here in a smaller scale, so you can experience it by yourself. So yeah, it should contain, the data should contain those 1,200 steps, yeah, which is here. And if we have that, we can then try to do something about it. But maybe before I do this, I would show you another thing. Because if you, let's say, get interested enough to start using Blender for some kind of data analysis or even some kind of tool development for Blender. So it is very convenient to use Visual Studio Code for that, because there is plenty of add-ons specifically developed for Visual Studio Code. And one of them is called Blender Development. So I might put it in the chat. I have I have this add-on already installed. So if you have that add-on, then you can basically directly interact through VSC code with Blender. And it is possible by installing the add-on and then using the shortcut Shift Command P or Shift I think Control P on Windows or Linux, and search for Blender, and it will provide you with all the possibilities that are being available through this add-on. And for example, or one of the main ones is Blender Start. If you hit that, so you can then locate your installed version of Blender and run it through Visual Studio Code. So if I do this, another instance of Blender will appear. And yeah. So it's this one. Yeah, this one, the empty scene or with just a box. And if you go back to Visual Studio Code and, for example, we try to run this script through Blender and get the results directly in Blender. So for that, can again go with Shift Control P, and in this case use Blender run script. And basically, it runs the script you have active in Visual Studio Code, which is this one. And you have probably noticed that I have already placed the breakpoint in that script. So in that way, you can already kind of start debugging the stuff, and you can also observe what is the actual state of variables in Blender and so on and so on. So very convenient way and much more easier, I would say, than the standard one through directly running something in a standalone instance of Blender. So basically, here it would just run the script and output the results, but through Visual Studio Code, you are even able to debug the thing and observe whether the values you are expecting in some variables are the correct one, and so on. Yeah, so basically, if I let it finish, it's in this Blender. So you can see that the code has loaded the data, which we stored previously, into those NumPy arrays and created the representative geometry for the data. And if I open the spreadsheet editor, which, as I said, is quite convenient for exploring this kind of data, you can see we again have values, and we stored those values as vertices. So you can see we have really 1,200 vertices with those attributes. Okay, so that was this thing, which I think is very convenient if you decide to start experimenting with developing your own stuff, or even trying to prepare some script that will process your data or load your data directly in Blender. So yeah, you can debug it directly through here. Okay, so I closed it, so the instance of Blender disappeared. So here I have just one instance. So if I go back to the data we have prepared, another blend file that is part of this data set is called geonodes.blend. And basically it continues on the stuff from the previous one, which was this one. So let me show it. And it already has some content created in the scene. And it's even live content. And yeah, basically it's the replication of the animation you saw at the beginning, but let's say in more advanced way, and with the possibility to add additional stuff onto it. For example, here you can see some trail after the massive object moves, and also an arrow that represents the velocity at the respective instance at the time of respective body, yeah, that moves. And all of that is being basically done by applying another very powerful tool in Blender that is getting more and more popular. It's called geometry nodes. And if I enlarge this area, so you can see that there is some structure of nodes. And those nodes represent some functionality that is being applied on whatever data you have in that specific object that you apply the geometry nodes on. So if we check this, so if we dig in more detail through the content of the scene, and specifically through the content or what's basically happening on particle number 1. So here you have some visual representation of geometry, so meaning that it's a mesh. So it has some data and some topology. There's this one. And another one is this icon, which represents in Blender application of a modifier. And a geometry node is a specific kind of modifier that you can apply on the data in Blender. And in this particular case, we are trying to, or we are applying a geometry node structure that is called motion on an object called particle 1. But we have 2 particles, so yeah, the same nodal structure is being applied also on the second particle. So as I said before the break, that we will continue with the concept of geometry nodes. So we have those two meshes that we loaded from a previous step into Blender. And those meshes keep the information about the movement of each individual mass together with some other additional stuff, such as velocity at every instant in time, and yeah, some other stuff which I will explain later. So on each of those two particles, I've applied a set of nodes, which I will try to explain right now. So it might look quite chaotic, but there is a system in that. Basically, you start with a set of group input. If you apply geometry node on any kind of mesh geometry in Blender, and group output. And this way, from the input to output, needs to be somehow connected. And what you put in between, it's totally up to you. So you can come up with your way of processing the data. So at the input, you have that information that is kept on the geometry. And on the output, you should provide some processed kind of geometry that you want your final result be or look like. And here in this example, we see that this is the final geometry. And because here you can see that I have particle 1 selected is being visualized by orange color in Blender. If I select particle 2, you can see that, and it looks different, right, than it looked before, which was just a bunch of points that represented the trajectory. And that's what happens when you apply some geometry node structure. I haven't checked. I hope you can hear me. Yeah. No complaints, so probably it should be all okay. So yeah, let's continue. So basically, let me now briefly introduce you into geometry nodes and explain what we have applied on initial geometry to arrive to the final result, which means some kind of mass representation here by a sphere with arrow representing the actual direction and size of a velocity vector, together with, if I play the animation, together with some tail that follows the direction of movement of that particular object. So we started, or we input the geometry nodes with mainly the information about the vertices and its attributes. So here, if I start with this block of nodes, basically we are taking from the geometry only points, or we want to apply something on the points. For this reason, we have here the node, which is called instant on points. And this node can basically put some additional geometry on that point or at that point. And here we have some object that is being placed as an instance to particular point. And here we see that we have bunch of points. So it's not just one point, which would be quite logic to have just one point because we see just one sphere, right? So we are kind of filtering what is being used as a point, and this is mainly provided with this connection. So basically we select just some specific point out of those set of 1,200 points, and at that selected point we add as an instance some object, and this object is provided from input. So here you can also see, well, maybe like this. You can also see that if I go within the properties editor, if I go to the modifiers setup, and because I have only one type of modifier on that particular object that is being selected, which is the geometry node modifier. So I can see the setup of that modifier. And basically with geometry nodes, you can kind of already create your own UI in Blender, because whatever is taken as an input into geometry node structure appears here as a value that you can change. Either it's a numerical value you can set through here, or you can because as I said previously, you can get Python tooltips, and basically whole Blender can be controlled by just Python. So you can even control it from somewhere else by using, as you can see right now, Python tooltip. So I can either read this value or change this value through Python. Yeah, this is also possible. But here, let's say, if I duplicate this, here, I just wanted to show that it is possible to partially hide or fully show what's the full content of a group input. And basically, it's the identical copy of what you can see in here. Here, just for clarity, typically we hide it. Yeah? So if it's not connected to anything, it doesn't show anything. Okay, as soon as I connected some of those inputs to something else and then hide it, it will stay just those connected nodes. But there is more of those. So that's what I wanted to show. So we can work with maybe let's go back. We can work with as many inputs as we define, let's say. And as you can see here, there is an empty slot. So this way you can easily create a new kind of input and then start working with that within Blender. So if I would connect it to something, then it would appear in that structure as well. And I would be able to name it as well. If you let's say open this sidebar by that arrow or by a shortcut key N, yeah, maybe Blender is very convenient if you learn some kind of initial set of shortcut. Those are very well documented in a lot of places. So yeah, some selected, mostly used set of shortcut you can find on the internet. and it makes it much more convenient for you to work with the Blender. But whatever you have under the shortcut is definitely also achievable through user interface as well. This was one example. Yeah, shortcut N opens it the sidebar through which you can then define basically the naming, yeah, of your input and output sockets and so on. So okay, let's continue so we don't waste the time. So here basically we are solving the problem of visualizing some kind of geometry instead or at the position, specific position at a time at some specific point. And this way we will create the animation. And as the main controlling knob here or input, there is used the selection input that we first need to somehow correctly set up. And for that, because we want to animate the stuff, so basically we want to add specific frame, which you can see here. So this is the timeline of the whole animation. So at specific frame, for example, right now I'm at frame 121. So you can check in here that, yeah, that's the actual frame. And in geometry nodes, you can use it as one of the available nodes. If you hit Shift and A. So here you have different kind of nodes. You can even search. So yeah, scene time is one of them. So you can then interfere with the scene time or use this variable within the geometry node structure, which we are using here as well. And basically at a specific frame, actual frame, which we use, we want to kind of filter out everything else and create this in this way selection for just one point that is then being used in this instance on points kind of node. So basically, as soon as I switch the frame, it selects different position of the particle or of the mass object. And this way we created basically the animation concept. So we control it by parameter of frame, actual frame. So that's this. Then we have some trail, which is this art. And for that, we are doing, let's say, simple arithmetic and Boolean operation. Yeah, I didn't mention in geometry nodes to more easily understand what is happening between those connections. So yeah, those connections have different meanings. Basically, the rounded or dot means that there should be a single value. Here, it's a single geometry you are working on. In case of diamond shape, typically it represents the field, which means in Blender that typically there might be some vector information or multiple values behind. So for example, here we have 1,200 points. And if we use the concept of fields and specifically the index, so the indexes of all the points, so we are able to kind of create a field of zero values except the one that is the same as the frame number. So for that index that has the same value as the frame number, we have Boolean value of 1. all the others are zeros, and this kind of field is being sent here. So basically, this way we are selecting just that particular point, and we instantiate object at that point location. With a similar concept, we kind of count several points back to be able to get the positions that happened already in the past, and with those positions kind of create additional geometry that represents the tail. So we have also some of those variables available as an input, so we can change them and control it this way. So for example, we can control the start of the tail this way, and also the length of the tail. And also the tail radius. So we can make it thicker or thinner, and basically you can create much more complicated structure that would then represent the tail. Yeah, it depends on what you really need. Yeah, and this is just a simple example. So basically we kind of filter out a bunch of points that have some coordinates in the space, and throughout those points that then will represent the tail, we do some conversion from mesh to points, because here as an initial geometry we have a mesh, and again we apply a specific selection for the tail, which we then get as a point, and those points are then converted to curves, and the curve is then being used as creating geometry to really get that conical shape for the tail. So basically we recreate the curve. We also set the radius of the curve, and here we are using spline parameter factor, because within the curve it's kind of ordered, and it has numbers for each individual point on the curve. So we can use it as a factor to control the radius of the curve, because it is another parameter that can be used as a or for the curve. And this way, yeah, basically we create that conical shape. So we mix the curve with the curved circle, and this curved circle and its radius is being controlled by this. Yeah, so that's why it's getting thinner at the end and thicker at the beginning. And we can also fill the cap. Yeah, so meaning if I go closer, so you can see now there is a it's not closed, the geometry. So if I fill the cap, you can now see that, yeah, it closed the geometry. So yeah, that's another kind of geometry that we are recreating over our data. Another important one, or what is being used here, is basically the arrow that represents the velocity of a particle at a particular instance in time. For this, because we want to correctly represent or map, which will be seen later, color for the magnitude of the velocity. So basically, let's say we want to have blue color when or yellow color, depends, but I think we set it this way, when the magnitude of the velocity is low, and red color when it is at its maximum. So basically, we use for that this set of nodes. So we are filtering out the velocity values from here, and from the whole data, we are sampling it at every index. So basically, we really take into account all the velocities. We are interested in their absolute value, because here we have a vector. So basically, yeah, we are really working with the magnitude. And here there is a node that provides the statistics for us. So basically, we are interested in the maximum. So basically, it finds the maximum magnitude of the velocity vector within the whole data set. And we use it as a normalizing coefficient throughout the length of that arrow, and we then use it. So basically, this value will be within 0 and 1, and this is then stored as a parameter at the output as val underscore col, which we will then use in a shader editor, and this way we will assign correct color depending on the length of the vector. Okay, so that's for the color of the velocity vector. And as for direction and all the other stuff, because we kind of created really an arrow with the cone and so on. So for that stuff, there is a bunch of additional nodes needed for that. So basically, again, we are taking out position at that particular instance in time, velocity at that instance, and we are basically recreating really an arrow. And we have some controlling values for that. So if I go back to those, so for example, here you can see that the arrow really correctly represents or respects the motion of the particle, and we can also tune it the way as we did for the tail. So we can move it a bit further. We can set radius. So basically, basic parameters of that additional geometry we created, and we can also set the multiplier that is being applied on the length of that vector. And yeah, we can also influence the tip of it. So all of that is basically available throughout geometry node. So even though it's kind of a simple example, it provides you, really full control and lots of additional stuff you can add to that. And maybe the last thing I want to mention in this respect is, for example, here, another quite nice node to use, which is called mesh to volume. So we can basically decide whether we want to represent the tail either as a volume object or mesh object. So basically here it inputs as a 3D surface topology or geometry, and we convert it to volume and set some material on that, similar to its surface representation. And here basically we have just a switch to select whether we want this or that. So if I switch here, which is quite important set of control knobs in Blender that are part of a 3D viewport editor. and those basically switch between different renderers and shading modes. So right now there is a viewport shading mode, but I can switch to material node, or I can even switch to render node. And depending on selected renderer, which is being selected throughout this editor, throughout the properties editor, in the render section. Right now we are using, it's called EV renderer. So it is a rasterizer, but quite powerful one that is getting better and better and can mimic a lot of stuff that were typically available only in path tracing engines. So yeah, the benefit of EV is that it is still quite fast, so you can use it for interactive visualization, but is able to visualize even complex effect already. Or you can go fully into path tracing, so by selecting this. And as I was mentioning at the beginning, if you also set up your Blender the way that if you have some accelerator available on your machine, if you tick it in here, you will then be able to select it also in here. So now I'm using GPU, metal GPU for rendering. And yeah, you can see the typical behavior of path tracing engine. So unless it's kind of finished in terms of samples per pixel, it is provided with some noise. And then when it stabilizes, it provides clear image. But why I started to talk about this is that I wanted to show you that, yeah, you can switch between different representation of the tail. Right now, I turned on the volumetric representation, which is smoother than the one represented by surface mesh that is using some emission or emissive shader on top. Yeah, so that's why lighting as a source of light. Okay, so that's this. Yeah, so if I should sum it all up or yeah, summarize it, what is happening in this geometry node structure. So basically, we introduce some representative geometry that represent the mass of each particle, and we add two main important geometries on top of that. One of them is the arrow that represents the velocity vector, and the other one is the tail that kind of represents the history of the movement of the particle. And all of that is being orchestrated by a set of nodes that always select just one particular instance from the whole data set in order to provide or create the animation of the whole phenomenon. And all of that is then being joined into one node and represented again as one single geometry on which we are also, we are also setting one additional attribute, which we are then using in a shader editor. So that's about it. And those objects have different shaders set on top of them that are being assigned directly through the geometry node structure. So, for example, I just show you, yeah, this one, because this one is important one. Shader named velocity.002 or material. So if I go to material editor, which is in here, and select that particular material in that editor, so I can see its structure. And again, it's another nodal structure in Blender, but specific for setting up the material or a shader. This material is specific for coloring the arrow that represents that velocity. And as I said, we basically normalize its magnitude between 0 and 1 in order and store this into a parameter or attribute called col, such as color, that was created in that geometry node structure. And we can use this parameter within shader editor, read it as an input, and let it control the values from color RAM and assign those colors or particular color based on this value as a base color of standard default, let's say, material in Blender, and assign it as a material output, which is then being applied in here. Yeah, so basically on that arrow, if I move a bit back and let's say check. So basically the only colors you should see on those arrows should be spanning from blue to red. So at the maximum, which is somewhere in here, you should see the red, and at its minimum, you should see the blue. Yeah. So it works. So it is matching correctly. For example, here. Yeah, when the arrow or the velocity is very small, it is really blue. So that's the concept behind an interconnection between, let's say, geometry node editor and also the shader editor in Blender. Yeah, now I wanted to speak a little bit of our voxelization concept that is part of our space converter we are developing within the space project. So let's say the simplest example we could find was that we applied the concept of voxelization on those two particles. So each of that particle, as was also mentioned at the beginning, has beside the position and velocity and mass also the value of SPH, which we are then using in that voxelization script. Again, it's not necessary to run the script because what this script does is that it generates the content of this folder. So it generates 1,200 VDBs, small ones, so not a big issue. Just to basically give you an idea how the voxelization works, and yeah, simply to understand the concept we are trying to apply on a particle data from SPH codes in a space project. So basically, again, if I go through the script quickly, so we are reading the particle data, which we created in the first step, in order to be able to voxelize it because we voxelize it as a one space, meaning both particles together in one space. So basically, at one instance in a time, we always get one VDB that covers both particles. So we need to know basically the bounding box in which those two particles operate in space. So we are checking some X, Y, Z minimas and maximas. On top of that, we also add some extra. So we enlarge this bounding box specifically by the amount of SPH value times some additional extra, which is called kernel support. So we enlarge this bounding box this way. We also set up the voxel spacing, meaning the distance between the voxels. So basically, at the end, it will influence the number of voxels in each particular VDB file. And we also, so why don't I maybe run it? Just for you to see what's behind. Because I'm using some specific Blender functionality, so I need to run it through that Blender development add-on in PSC code in order to be able to basically go through individual steps. And run that script. So yeah, we are setting some ranges for that bounding box, and at the end, because we are using that voxel spacing value, so basically we set the ranges respective to voxel spacing. So it is always in the multipliers of 0.1. So this way we align the space around those two particles. We also need to mark the offset in order to correctly match this way created the space, which we voxelize for later use in Blender when we basically import that created VDB files in Blender again, so they match with the structure of those particles. And basically, what we are up to is that we want to visualize around those particles, smoothed region of spherical shape that will represent selected quantity of that particle, and in our case, it will be mass. So basically, the value of mass will be represented as a volumetric object. Yeah, and basically for that we are using or we can use two quite simple kernel functions that basically smears out the value of the mass from its origin around its closest region based on the value of SPH parameter. So the higher it is, the more smooth and larger the output would be. So that's the initial concept behind. And what is important and what I wanted also to point out is that the Blender is already provided with OpenVDB library, and we are using that to create the volumetric representation of such quantity. So you can already use it in the similar manner in case you want to kind of convert some particle-based output into volumetric output. Of course, it's not purposed for really heavy load of millions of particles, but if you want to test and try in a small scale, it is already available and you can use it. Yeah, so basically, it will convert into volumetric format. There are a bunch of for loops. We are generating individual VDB file for every step. So out of those 1,200, so that's one loop. Then there are two particles, so we iterate over two particles. And of course, we have to iterate, that's the main iteration, that converts or calculates using that kernel function and populates the closest voxels around that particle with calculated value that comes out from that kernel function. So this way it basically fills the regular grid of a PDB file with respective correct values, meaning at the center it should have, the kernel function should have the value of 1, so basically exactly representing the voxelized or kernelized quantity we want to process this way. And as I said, in our case, it's a mass. And yeah, here it is. So basically, this way it creates VDB files. And if I then open other blend file which we prepared for that, it should be the scene final. So here you can already see some foggy areas around those two particles. And you can also see that in scene 3, there is a new object, which is called volume underscore step underscore 000. You can check in more detail what's this object about. And for specifically volumetric objects, if you have in your scene this kind of object, so for example, you can see the difference in here in a properties editor. If I select standard surface mesh, you have some possibilities to see the details and different setup of that object, which is a bit different in case of volumetric object. In that case, this icon appears, and through this setup you can check in more detail what this object is about. And in our case, we basically added in the scene this kind of object. You could do it manually by basically either using this menu, add, and then selecting volume and import OpenVDB file. In that case, yeah, you would have to directly select the OpenVDB volume, or in other case, just an empty. So here it created another volumetric object, and you can set it later similar way as we already have this one. So let me just delete this one and check again the other one. And in Blender by default, you can point Blender where to look for that particular VDB file. And if you have a sequence of such VDB files, so Blender by default recognize that. And if you kind of stick with simple naming convention, so you name your VDB files um, um, with the using numbers, ascending numbers. So basically, those then represent the sequence of such VDB files. So basically, you can then set the tick for VDB sequence in Blender and set the range for those, and then it correctly matches with your, let's say, animation. So as you can see, we already have some volumetric animation in Blender. And basically what it does, again, main control value is number of frame. So it kind of searches for this value in that folder with the VDB sequence and reloads that VDB file or visualize that VDB file that corresponds with that number of frame. That's basically the all magic behind that. So if you create your VDB sequence in that manner, you are then able to visualize it directly. And basically that's again EV renderer, which is automatically turned on when you turn the material preview. But we can switch to cycles as well, and maybe check in more detail. So yeah, here is the representation of the particle as a volumetric object. And as for that, another important thing is how we set the shader for this. So yeah, in that respect, we are using material called material, which is visible in not in here, but yeah. If I select the object, then I am immediately being shown what material it uses. So yeah, for low values of a mass, it uses blue color and red color for maximum values. So in the center, it should be red. At the boundary or at the end of the SPH radius, it should be blue. And it's a volumetric object, so it is using principled volume shader or material that is a basic material in Blender that is being used for volumetric objects to correctly visualize them. And as such, you can, or we have basically went through all the steps in order to visualize this kind of simulation. And here you can see the final output, which we rendered from that simulation using cycles renderer. Yeah, and you can see the interaction of the light. Maybe just to speak a bit more about setting the light or lights in the scene. There is another useful and important concept in shader editor in Blender. Either you can select object, so basically you are checking what material is being applied on a selected object, or you can switch to world setup, and in that case you can set up kind of model for global illumination of the scene this way. And in that particular case, we are using so-called sky texture that basically represents similar lighting conditions as you can get from outside during the day. And here we have just some specific setup in order to have black background when we are observing the final visualization throughout the 3D viewport. So yeah, that's something specific, but basically this node is the most important, and this basically integrates the global illumination model in Blender. So if I tweak with those values, I can make it darker or lighter. Okay, and let me just quickly jump to the last scene. Which is this one, Open Gadget Visualization .blend. Basically, it's a prepared scene with a small data set we got from Luca Tornatore from Open Gadget Code. And what we wanted to show you here is basically in more detail what you can do in a shader editor, and yeah, how you can influence the final visual of the scene, as well as with again setting up the world. Yeah. So here, yeah, no specific conditions are being used. So for the world, so basically all the lighting is being set up through shader editor. So if I switch back to that and select the object of my interest, which is another volumetric object, similar to the previous one, but this one was obtained, as I said, from Open Gadget Code, and it should represent a cluster of galaxies. And as such, we have converted it using Space Converter and basically created a VDB file that contains three important grids. One is gas density, another one is gas internal energy, and the last one is star masses. And you can see that it changes when I switch between one and another. And if I turn on the render by switching to different shading, and here in render setup, I have selected cycles with GPU support. So you can see that we can already visualize the phenomena and quite interactively. The blurriness, the beginning is caused by, not enough rays being traced, and also As you can see, I haven't mentioned that, but yeah, now I can mention it. Basically, what it corresponds, the setup of the renderer for this viewer is set in here. So sampling for the viewport, and I also have ticked the denoise. Yeah. And behind that, there is basically neural network approach that is being applied on a noisy preliminary result like this, in order to provide the user with more nicely looking output sooner than the renderer ends its job. So it is another quite speeding tool in terms of visualizing the output.
What kind of denoisers do you have available?
I think it's open image
Oh.
denoise. But for NVIDIA GPUs, there should be also yeah. But I don't have this one. Well, because I'm on Mac, so yeah, it provides only this one.
They are based on machine learning.
Yeah. Okay, so if I speak just briefly about what's in the shader. So I mentioned that the data set now in VDB has 3 grids. One represents the gas density, another one gas internal energy, and last one star masses. So we can work with those directly in a shader and basically use those grid to kind of create the final setup of the shader, meaning that by using one grid we can attenuate some values from that stored values or other way around, and basically set up it the way that it really shows the user what's the most important. Very often it's trial and error process, but as soon as you get used to it, it's easier, definitely. So what I wanted mainly to show is that it is possible to create quite advanced type of shader by mixing values from all of the grids and providing the final output such as this. And if I, let's say, just show you that it really interacts. So sorry, by maybe turning off by muting this branch, turning off this emission kind of branch. You can see that those small dots that were lighting before disappeared. Now they appeared again. So yeah, you can this way basically visualize this kind of content, in this case star masses, so basically the stars. And since we are using emission shader, we are forcing the stars to emit some light and influence the final visual output this way. With that, I think I have said everything I wanted. Maybe let me check whether there are some questions. Doesn't seem so. So do you have any questions regarding either this topic or some of the previous ones? So if not, it's all from my side, and thanks.
Well, thank you everyone. Thank you those at home for attending. I hope you enjoyed the workshop and take something with you on the way back home. I want to ask you to please, if you haven't signed the attendance paper, it's important because otherwise you won't get the certificate of attending. Also, we have shared a poll on what do you think about the workshop via email. Please answer because that's useful for us to keep improving.